Every single second, the universe expands, unfurling mysteries so profound that they challenge our very existence. What if there is life beyond our blue planet? What secrets do the stars hold about the origins of our universe and our place within it? Join us today as we delve into the biggest mysteries in the universe. Some of the most intriguing phenomena in the universe are black holes, regions in space where gravity is so strong that even light can't escape. Formed when massive stars collapse under their own gravity, black holes warp space and time around them. At their boundary, the event horizon, everything changes. Beyond this point, our current understanding of physics breaks down, leaving us with many questions about what lies inside. Another extraordinary occurrence is the phenomenon of neutron stars. These stellar remnants are incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh as much as all the people on Earth combined. The intense gravitational forces in neutron stars create a state of matter known as degenerate matter, where protons and electrons merge to form neutrons. They also give rise to pulsars, spinning neutron stars that emit beams of radiation, appearing to pulse as they rotate. Observing how these dense objects behave challenges our current theories of matter and forces. Dark matter also presents a significant puzzle. Although it constitutes approximately 27% of the universe's mass-energy content, it remains elusive, detectable only through its gravitational effects on visible matter. This intangible mass influences the rotation of galaxies and the formation of large-scale structures in the universe, leading scientists to question what it truly is and how it interacts with ordinary matter. The search to uncover the nature of dark matter pushes the boundaries of physics and forces researchers to reconsider existing models. The phenomenon of cosmic acceleration brings us to a frontier of mystery. Observations reveal that the universe's expansion is not only ongoing but is accelerating. This breathtaking discovery necessitates the inclusion of a form of energy known as dark energy, which constitutes about 70% of the universe's content. Dark energy's properties and origins remain one of contemporary cosmology's most substantial enigmas, fueling discussions about the fate of the universe and the fundamental forces at play. Each of these remarkable phenomena invites us to delve deeper into the cosmos, questioning what we know and exploring the mysteries that lie beyond our current understanding of physics. The discovery of exoplanets, or planets that exist outside our solar system, fundamentally alters our understanding of the universe. For many years, the notion of other worlds populated with potential life was confined to the realm of science fiction. However, the realization that there are billions of stars, each possibly hosting multiple planets, radically expands the scope of our cosmic neighborhood. Astrophysicists estimate that in our Milky Way galaxy alone, there could be as many as 100 million planets within the habitable zone, where conditions may be just right for the existence of liquid water, a vital ingredient for life as we know it. This highlights the possibility that we are not alone, and that there may be numerous places across the cosmos where life could exist, thriving in environments very different from our own. The diversity of exoplanets discovered thus far has shattered previous preconceptions about what planetary systems can look like. From gas giants that orbit their stars at blistering speeds to Earth-like planets situated in the right conditions for life, these discoveries encourage scientists to rethink planetary formation theories. They reveal an astonishing variety of atmospheres, terrains, and potential habitability, each offering unique insights into the processes that govern planetary development. As researchers continue to explore these distant worlds, they are also refining the technologies and techniques used to study them. This growth in knowledge not only enriches our scientific understanding, but also stirs our imagination, inviting us to ponder the mysteries that lie beyond our own planet. The journey to uncover the secrets of exoplanets reshapes our perspective, igniting a sense of wonder about the possibilities that the universe holds. Galaxies, the vast collections of stars, gas, dust, and dark matter, are categorized into several distinct types, each possessing unique features and structural attributes. The three primary categories are spiral galaxies, elliptical galaxies, and irregular galaxies. Spiral galaxies, like our own Milky Way, are characterized by their well-defined arms that spiral outward from the center, containing younger stars and abundant gas and dust. This structure allows for ongoing star formation, creating stunning nebulae and clusters. Elliptical galaxies, on the other hand, exhibit a more rounded, smooth appearance. They range from nearly spherical shapes to elongated ovals and are primarily composed of older stars, with minimal gas and dust. This leads to a lack of ongoing star formation within these galaxies. Elliptical galaxies are often several billion years old, demonstrating a peaceful but less dynamic nature compared to their spiral counterparts. Irregular galaxies defy this clear-cut categorization. They appear chaotic and do not have a distinct shape, containing large amounts of gas and young stars. Star formation is actively happening in these galaxies, often triggered by gravitational interactions with nearby galaxies. This category includes some fascinating examples like the Large Magellanic Cloud, a companion to our Milky Way. As scientists study these different types through powerful telescopes, new insights emerge about their formation and evolution. Each type of galaxy serves as a window into understanding the cosmos, revealing how these magnificent structures have provided a home for countless stars and planetary systems throughout the universe's history. The formation of black holes begins with the life cycle of massive stars. When a star exhausts its nuclear fuel, it can no longer counteract the force of gravity. In a dramatic finale, it may undergo a supernova explosion, shedding its outer layers into space. The core that remains, if it is sufficiently massive, collapses under its own gravity. This results in a point of infinite density known as a singularity, surrounded by an event horizon, which marks the boundary beyond which nothing can escape, not even light. The enigmatic nature of black holes stems from the very essence of their existence. They challenge our understanding of physics, particularly at the intersection of general relativity and quantum mechanics. Scientists describe their gravitational pull as immense, yet what lies beyond the event horizon remains a mystery. Information that crosses this threshold appears to vanish, igniting debates among physicists about the fundamental concepts of space, time, and reality. Moreover, black holes can be of different sizes. Stellar black holes form from the remnants of massive stars, while supermassive black holes containing millions or even billions of solar masses exist at the centers of most galaxies. These phenomena not only evade conventional understanding, but also play a pivotal role in the evolution of galaxies, influencing their formation and growth. The quest to comprehend black holes fuels ongoing research. Scientists employ advanced observational techniques, such as gravitational wave detection and imaging events like the one captured by the Event Horizon Telescope, which provided the first glimpse of a black hole's shadow in the galaxy M87. Each discovery adds a piece to the puzzle, revealing the complexities of a universe governed by forces far beyond our current reach of understanding. Dark matter is a vital component in the architecture of the cosmos, influencing the formation and behavior of galaxies in profound ways. While it is invisible and does not emit light, its presence is inferred from the gravitational effects it has on visible matter. Observations reveal that galaxies are surrounded by vast halos of dark matter, which significantly affects their structure and evolution. Without dark matter, the speed at which stars orbit the centers of galaxies could not be explained. The gravitational pull of dark matter helps to hold galaxies together, preventing them from flying apart despite the rapid movement of their stars. As galaxies formed in the early universe, regions with higher concentrations of matter began to collapse under their own gravity. Dark matter played a crucial role in this process, acting as a scaffold around which normal matter could clump together. This gravitational framework allowed gas and dust to coalesce, forming stars and other celestial bodies. Therefore, the existence of dark matter not only facilitates the birth of galaxies, but also contributes to the formation of large-scale structures in the universe, such as galaxy clusters. Observations of cosmic phenomena further demonstrate dark matter's dominion over galactic behavior. For instance, when we look at the rotation curves of spiral galaxies, the rotational speeds of their outermost stars contradict predictions based solely on visible matter. This discrepancy indicates that there is much more mass present, mass that we cannot see. The gravitational influence of dark matter within these galaxies ensures they maintain their structure over billions of years. Furthermore, dark matter may help explain the dynamics of galaxy collisions and mergers. In these cosmic events, the gravitational interactions are not limited to visible matter. The unseen dark matter plays a crucial role in determining the outcome of these galactic encounters. As galaxies collide, the dark matter halos surrounding them interact, affecting the merging process and how the resulting galaxies ultimately evolve. Together, these observations not only highlight the importance of dark matter in shaping galaxies, but also underscore the mysteries it still presents to scientists seeking to unlock the secrets of the universe. Astrophysicists employ a variety of ingenious techniques to study phenomena that remain beyond the limits of visibility, such as dark energy. At first, dark energy might seem elusive, as it does not emit, reflect, or absorb light. However, scientists have found that its presence can be inferred through its gravitational effects on visible matter, radiation, and the very structure of the universe itself. One of the primary methods used to probe dark energy is through the observation of distant supernovae. These stellar explosions serve as cosmic candles, providing critical insights into the expansion of the universe. When astrophysicists analyze the light from these supernovae, they can compare the observed brightness to their known intrinsic luminosity. This comparison reveals that the universe is expanding at an accelerating rate, a phenomenon attributed to dark energy. Additionally, large-scale surveys of the cosmos, such as the Sloan Digital Sky Survey, measure the positions and brightness of millions of galaxies. By examining the distribution of these galaxies and how they cluster together, researchers can infer the influence of dark energy on cosmic structure formation over time. The observation of baryon acoustic oscillations, which are regular fluctuations in density, further aids in understanding how dark energy shapes the universe. Cosmic microwave background radiation is another crucial piece of the puzzle. It is the afterglow of the Big Bang, and its subtle variations across the sky provide vital clues about the universe's early conditions. By analyzing these variations, astrophysicists can glean insights into the density and composition of dark energy. Each of these methods, combined with the power of sophisticated simulations, allows scientists to piece together the mystery of dark energy, unraveling the secrets of the universe's expansion and its ultimate fate. Gravitational waves are ripples in the fabric of space-time, produced by some of the universe's most violent and energetic events, such as the collision of black holes or neutron stars. Albert Einstein first predicted their existence in 1916 as part of his general theory of relativity. This groundbreaking theory describes how mass and energy warp space-time, and it was a novel idea that suggested incredibly massive objects could create disturbances that travel across the cosmos. The significant aspect of gravitational waves lies in what they reveal about the universe. Unlike light waves, which can be blocked or absorbed by matter, gravitational waves can pass through everything unhindered. This property allows scientists to gain insights into celestial phenomena that were previously hidden from view. The detection of these waves has opened up a new way of observing the universe, leading to what many refer to as gravitational wave astronomy. By studying these waves, researchers can better understand events like the merging of black holes and the life cycles of stars. The first successful detection of gravitational waves took place in September of 2015. The Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, captured the waves produced by the merger of two black holes located more than 1 billion light-years away. This monumental achievement not only verified Einstein's predictions, but also marked a new era in astrophysics. Scientists around the world were able to pinpoint that moment, confirming that two black holes, each roughly 30 times the mass of the Sun, spiraled together and merged, creating a single, more massive black hole. This initial discovery was a thrilling moment for the scientific community. revealing that gravitational waves could provide a unique window into the events following the birth of black holes and the delicate dance of cosmic bodies. The ability to detect these waves has since expanded, with additional instruments and observatories joining the quest to observe and analyze the messages these waves carry from deep within the cosmos, helping to illuminate the secrets of our universe. Rogue planets are celestial bodies that wander the cosmos without being tethered to any star. Unlike planets that orbit stars, these intriguing objects may have formed around a star before being ejected due to gravitational interactions. Some estimates suggest that there could be as many rogue planets as there are stars in the galaxy, an astonishing thought that expands our view of planetary systems. The mechanisms behind their ejection are fascinating. During the formative years of a solar system, young planets can interact violently with one another. Collisions or close encounters can alter their orbits dramatically. When such a planet gains enough energy from these interactions, it can be flung away into interstellar space, detached from its stellar parent. Equally compelling is the possibility of rogue planets forming in isolation. These planets might develop from the cold gas and dust that permeate space, coalescing into solid bodies far from the heat and light of a star. This process remains a topic of active research, as scientists look to understand the conditions that allow for planet formation in such chillingly distant environments. These solitary travelers can be intriguing to study. Without the glare of a star to illuminate them, they can be difficult to detect. Yet recent advancements in technology are revealing new techniques to study these elusive planets. Understanding rogue planets not only sheds light on how planets can exist apart from stars, but also raises questions about the potential for life in places we least expect. Supernovae are extraordinary cosmic events marking the explosive death of massive stars. When these stars have exhausted their nuclear fuel, they undergo a collapse under their own gravity, leading to a catastrophic explosion. This explosion is not just a spectacular display in the cosmos. It plays a crucial role in the synthesis of elements that are vital for life as we know it. During the intense heat and pressure of a supernova, nuclear reactions forge new elements. The process produces a variety of heavier elements, such as carbon, oxygen, nitrogen, and iron. These elements are fundamental building blocks of life. For instance, carbon is the backbone of organic molecules. Oxygen is essential for respiration, and nitrogen is a key component of amino acids and nucleic acids. Without these elements, the complex chemistry necessary for life would simply not be possible. Once the supernova finishes its explosive display, the remnants disperse these newly formed elements throughout the universe. This stellar debris enriches the surrounding interstellar medium, providing materials for new stars and planets to form. It is within these new celestial bodies that the elements collected from ancient supernovae come together to create the conditions suitable for life. Thus, supernovae are not merely the dramatic conclusion of a star's life, they are essential events in the grand cosmic cycle that fosters the creation of life itself. Without these colossal explosions, the universe would lack many of the essential ingredients that have contributed to the emergence of living beings on Earth and potentially elsewhere in the cosmos. The cosmic microwave background radiation is a remarkable relic from the early universe, offering a glimpse into its infancy. This radiation, which fills the universe, is a faint glow that originated about 380,000 years after the Big Bang, marking a pivotal moment when the cosmos cooled enough for atoms to form. As these atoms began to coalesce, the universe became transparent to radiation, allowing light to travel freely. What we observe today is a snapshot of that moment, a canvas depicting the temperature fluctuations that eventually led to the structure of galaxies and clusters we see today. These slight variations in temperature within the cosmic microwave background radiation are not merely random noise, they hold clues to fundamental questions about our universe. For instance, they indicate the density of matter and energy at that early stage of existence. By studying these fluctuations, scientists can infer details about the composition of the universe, including the proportions of regular matter, and dark energy. Surprisingly, The maps created from this radiation suggest that over 70% of the universe consists of dark energy, an enigmatic force driving its accelerating expansion. Moreover, the cosmic microwave background poses profound questions regarding the nature of the universe's geometry. The data shows that the universe is remarkably flat on a large scale, which leads to intriguing implications about its ultimate fate. Will it continue expanding forever, or is there a possibility it could contract? Each discovery related to the cosmic microwave background reveals layers of complexity and deepens our understanding of cosmic evolution. Exploring this ancient radiation also poses a mystery surrounding inflation, a rapid expansion of space that is believed to have occurred just a fraction of a second after the Big Bang. The patterns within the cosmic microwave background may provide evidence for this theory, offering insights into how the universe came to be structured in a way that promotes galaxy formation. As scientists continue to analyze this faint glow, they open doors to understanding not only the universe's past, but also the fundamental laws that govern its existence. String theory represents a bold leap into the attempt to unify the fundamental forces of nature. At its core, string theory posits that the most basic building blocks of our universe are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in different ways, and each vibration corresponds to different particles, suggesting a multitude of possibilities for how matter and energy behave. The implications of this concept are profound. If string theory holds true, it would provide a framework capable of integrating both quantum mechanics and general relativity. This is a monumental challenge in modern physics, as these two pillars of science have remained largely incompatible. By reconciling them within the string framework, we could achieve deeper insights into the fundamental structure of space-time, potentially revealing new dimensions beyond the familiar three-dimensional space and one-dimensional time that we experience daily. Additionally, string theory has led scientists to explore ideas of parallel universes and additional dimensions. Some versions of string theory suggest that our universe could be just one of many, with strings vibrating in different ways, possibly giving rise to entirely separate realms of existence. This multiverse concept challenges our traditional understanding of reality and opens new avenues for inquiry into the nature of existence itself. Moreover, string theory introduces the tantalizing possibility that gravity, electromagnetism, and nuclear forces may be different manifestations of the same underlying principle. If proven, this would revolutionize our worldview, illustrating that the same strands of cosmic yarn weave together the grand tapestry of the universe. Each revelation brings us closer to answering some of the most profound questions about the origins and workings of everything we see around us. The multiverse theory presents a fascinating framework for understanding some of the perplexing anomalies found in quantum mechanics. At the heart of quantum mechanics lies the concept of superposition, where particles can exist in multiple states simultaneously until they are measured. This mysterious behavior gives rise to a multitude of interpretations within the scientific community, as it challenges the traditional notions of reality. According to the multiverse theory, rather than collapsing into a single state when observed, the universe branches into countless parallel realities, each representing a different outcome of a quantum event. This idea suggests that all possible outcomes of quantum measurements actually occur, but in separate, non-communicating universes. For instance, when a particle is measured, the universe divides into one where the particle takes one specific value and another where it takes a different value. This branching forms a vast ensemble of universes, often referred to collectively as the multiverse. Many physicists argue that this model helps to address the so-called measurement problem in quantum mechanics. The measurement problem concerns how and why quantum systems appear to behave differently when we observe them. By proposing that each measurement results in a split into different realities, the multiverse provides a means of reconciling the strange behavior of particles with our everyday experiences of a definite outcome. Critics of the multiverse theory point out its speculative nature, emphasizing that it may complicate rather than clarify our understanding of quantum phenomena. Despite this, the multiverse has garnered substantial attention and interest as it invites us to reconsider the very nature of reality. In doing so, it underscores how much we still have to learn about the universe at its most fundamental level, leaving us to ponder the implications of an infinity of parallel worlds existing alongside our own. The concept of time travel has intrigued scientists and enthusiasts for generations, sparking a wealth of theories that stretch the boundaries of our understanding of physics. One of the most prominent theories is rooted in the fabric of space-time itself, a four-dimensional continuum that merges the three dimensions of space with time as a fourth dimension. According to Albert Einstein's theory of relativity, as objects move closer to the speed of light, time dilates, meaning they experience time at a different rate than those remaining stationary. This principle raises intriguing possibilities about the nature of time and how it might be manipulated. Another compelling theory arises from the idea of wormholes, which are hypothetical passages through space-time that could connect distant points in the universe. Imagine a tunnel with two openings, each situated in different times or locations. While the existence of such structures has not been confirmed, they are rooted in the mathematics of general relativity. If they could be created or found, they might allow for instantaneous travel across vast distances or even back in time, although the stability of a wormhole remains a significant concern based on our current understanding of physics. Quantum mechanics also introduces thought-provoking concepts related to time travel. The many worlds interpretation suggests that every decision creates a branching universe, leading to a multiverse of possibilities. This raises questions about how time travel might interact with these alternate realities. For instance, if one were to travel back in time and alter a significant event, would it create a new timeline entirely, separating it from the original? This idea fuels speculation and debate among physicists regarding paradoxes, such as the famous grandfather paradox, which questions the implications of encountering one's own past. In addition to these theories, philosophical considerations come into play when discussing time travel. The nature of causality, the relationship between cause and effect, and the very definition of free will become intertwined with the concept of traveling through time. As research in physics continues to evolve, our understanding of time travel remains rooted in theoretical speculation, but it challenges us to rethink not only our universe, but also the nature of existence itself. Wormholes, theoretical passages through space-time, hold the tantalizing potential to revolutionize how we think about interstellar travel. These enigmatic structures, often depicted as shortcuts connecting two distant points in the universe, could allow spacecraft to bypass the immense distances that separate stars. Instead of traveling across vast cosmic stretches, navigating around stars and galaxies, a wormhole might enable a much quicker journey from one solar system to another. The concept stems from the equations of general relativity, which describe gravity as the bending of space-time by mass. Imagine two ends of a tunnel, one at our solar system and the other near a distant star. If a wormhole could be formed and stabilized theoretically, it could contract the distance that separates these points, allowing ships to emerge in another star system almost instantaneously. This defiance of conventional space travel hinges on an understanding of exotic matter, a hypothetical substance needed to keep a wormhole open. However, the challenges before us are monumental. Creating or discovering a stable wormhole would require technology and materials that are currently beyond our reach. Moreover, the stability of such a structure poses significant concerns. Any disturbance could cause it to collapse, potentially trapping or harming anything within. Delving deep into physics and cosmology, researchers are exploring these concepts, juggling the tantalizing prospects of wormholes with the realities of current scientific understanding. Even though wormholes remain a topic of theoretical exploration, their study inspires innovative thinking about the universe. If, one day, we can unlock the secrets of these extraordinary phenomena, interstellar travel could move from the realm of science fiction into the realm of science fact, drastically changing the horizon of human exploration. What an incredible thought that is, as we gaze into the stars. The holographic principle represents a fascinating concept in theoretical physics that suggests our three-dimensional universe might be an illusion, much like a hologram. This idea emerged from the study of black holes and quantum gravity. When scientists attempted to understand the information contained within a black hole, they discovered that all the information could potentially be encoded on its two-dimensional surface rather than within its three-dimensional volume. This led to the groundbreaking suggestion that the entire fabric of our universe could be represented on a lower dimensional boundary. One of the implications of the holographic principle is the relationship between gravity and quantum mechanics. Traditionally, these two fields have been difficult to reconcile. Gravity governs large-scale structures, such as stars and galaxies, while quantum mechanics rules the behavior of particles at the atomic and subatomic levels. The holographic principle hints at a deeper connection between these realms, indicating that our perception of three-dimensional space might emerge from more fundamental two-dimensional information. Furthermore, the holographic principle raises profound questions about reality itself. If all the information about everything that happens in our universe can be traced back to a lower dimensional source, this challenges our conventional understanding of dimensions and the nature of existence. It suggests that our perception of depth and solidity might merely be an emergent phenomenon, leading to exciting inquiries into the nature of time, space, and consciousness. Researchers and theorists continue to explore the holographic principle's implications, seeking a more unified understanding of the universe. This principle not only deepens our understanding of black holes, but also inspires ongoing dialogue about the nature of reality. As we venture further into the mysteries of the cosmos, the holographic principle remains a captivating topic at the intersection of physics, philosophy, and our fundamental understanding of existence. The concept of parallel universes has the potential to profoundly challenge our understanding of reality as we know it. In the realms of physics and cosmology, the idea posits that there are multiple, perhaps infinite, universes existing alongside our own. Each of these universes can possess different physical laws, constants, and histories, which raises fundamental questions about the nature of existence and what it means to be real. Imagine a universe where events unfolded differently, perhaps one where certain historical figures made different choices. This notion suggests that every possible outcome of every decision could lead to a distinct universe. In this sense, parallel universes offer a canvas on which every possibility is played out. The implications of this are staggering, as it not only broadens the scope of what we consider reality, but also invites philosophical discussions about fate, choice, and consequence. This concept also emerges from scientific theories, particularly quantum mechanics. The many worlds interpretation proposes that every quantum event branches off into different realities. For instance, when a particle could behave in multiple ways, each possible outcome actually occurs, resulting in a split into new universes corresponding to each scenario. Such ideas stretch the limits of our current understanding of time, space, and the very fabric of the universe. As scientists grapple with these extraordinary ideas, they confront the challenge of testing the existence of these universes. While the theoretical framework is enticing, the inability to observe alternate realities directly leaves many unanswered questions. The pursuit of evidence or the means to manipulate and connect with these parallel realms continues to inspire groundbreaking research. It invites us to reconsider the singularity of our experience and beckons a deeper exploration into the mysteries of existence. The concept of a cyclic universe suggests that the cosmos undergoes endless cycles of expansion and contraction, rather than being bound to a singular beginning and eventual end. This idea has gained traction due to intriguing observations in cosmology. One significant piece of evidence comes from the study of the cosmic microwave background radiation. This ancient remnant of the Big Bang carries information about the early universe's conditions. Analyzing its patterns, scientists have found hints of spatial anomalies, which might suggest previous cosmic events preceding our current expansion. Another line of evidence is the behavior of galaxies. Over vast spans of time, structures within the universe can appear to have undergone transformations, suggesting a dynamic process rather than a static linear progression. This can be seen in the distribution and evolution of galaxies and galaxy clusters. Some scientists argue that patterns of galactic formation and collision indicate that they are not merely the result of a single expansion, but could be influenced by previous cycles, leaving behind traces of their formation in earlier epochs. Additionally, theoretical models based on string theory and quantum gravity propose that the forces governing the universe may allow for cyclic behavior. These frameworks offer mathematics that predicts a universe bouncing back from a contracting phase, potentially allowing for an infinite series of expansions and contractions. Although these theories remain speculative, they provide an attractive narrative that aligns with some astrophysical observations, suggesting that the universe may not have started merely at the Big Bang, but instead could be part of an eternal series of transformations. Furthermore, the current accelerated expansion of the universe raises questions about its ultimate fate. If the universe continues to expand forever, it may lead to a scenario termed the Big Freeze. However, alternate models suggest that gravitational forces could eventually counteract this expansion. Should such forces overcome the momentum of expansion, they could usher in a contraction phase, leading to another Big Bang. This interplay of forces illustrates a possible pathway that supports the cyclic universe hypothesis, urging us to contemplate the universe's true nature and its endless possibilities. Quantum entanglement presents a fascinating departure from classical interpretations of distance and communication. At the heart of this concept lies a phenomenon where two particles become intrinsically linked, regardless of the space separating them. This means that a change in the state of one particle will instantaneously affect the state of the other, no matter how far apart they are. This peculiar relationship challenges our everyday understanding of communication, which is inherently limited by the speed of light. Classical physics governs most of our tangible experiences and relies on established principles where information travels through space and takes time to traverse distances. For instance, a message sent from one point to another can only travel as fast as the medium allows, whether it be sound waves in air or light in a vacuum. However, quantum entanglement reveals a strange reality where this temporal limitation does not apply. When two entangled particles are measured, their states are determined simultaneously, suggesting a connection that defies conventional distance constraints. One notable experiment that illustrates the perplexities of entanglement is the famous Bell's theorem. This theorem proposes that if local realism holds true, the measurements of entangled particles should correlate in a manner predicted by classical physics. However, experiments consistently show results that align with quantum mechanics, revealing correlations that cannot be explained without acknowledging the non-local nature of entanglement. Thus, the implications stretch far beyond simple communication, hinting at a deeper, interconnected fabric of reality. This defiance of classical interpretations not only fascinates physicists, but also opens the door to practical applications. Quantum entanglement is fundamental to advancements in quantum computing and cryptography. These fields leverage the unique properties of entangled particles to develop technologies that could revolutionize information processing and secure communication. As our understanding of entanglement deepens, so too does the potential to redefine the limits of human connection and knowledge across vast distances. Dark energy is a mysterious force that plays a crucial role in the expansion of our universe. Since the late 20th century, observations of distant supernovae have revealed that the universe is not just expanding, but that this expansion is actually speeding up. This acceleration can be attributed to dark energy, which seems to counteract the gravitational pull of matter. One way to understand the influence of dark energy is through its presence in the fabric of space itself. As the universe expands, more space is created between galaxies. Dark energy exerts a sort of negative pressure that drives this expansion. Unlike gravity, which attracts, dark energy seems to have an effect that pushes galaxies apart, leading to an increase in the rate of their separation over time. This phenomenon challenges our previous understanding of the universe's fate, suggesting that it will continue to expand indefinitely. Scientific models propose that dark energy makes up about 70% of the total energy density of the cosmos. One prominent theory, known as the cosmological constant, posits that dark energy remains constant throughout the universe's history. However, other theories suggest that dark energy could change over time, influencing the expansion rate in different ways. These competing ideas illustrate the complexities of understanding this elusive force. While the precise nature of dark energy remains one of the most compelling puzzles in cosmology, its effects are evident. The patterns of cosmic microwave background radiation and the distribution of galaxies serve as evidence of how dark energy shapes the universe. As researchers continue to study these phenomena, our grasp of dark energy's role will deepen, revealing more about the fate of the cosmos and our place within it. The fate of the universe has long intrigued scientists and thinkers alike. Among the leading hypotheses, one prominent theory is known as the Big Freeze. This scenario suggests that as the universe continues to expand, galaxies will drift further apart, and stars will eventually exhaust their nuclear fuel, leading to a cold, dark, and empty cosmos. In this future, all matter will struggle to survive in a nearly lifeless state, with only scattered remnants of stars and planets remaining. Another compelling idea is the Big Crunch, which posits that the expansion of the universe could eventually halt and reverse due to gravitational forces. If this scenario unfolds, galaxies will draw closer together until they ultimately collide and merge. This dramatic process could result in the universe collapsing back into a singularity, a point of infinite density reminiscent of its origin. Such a fate places cosmic cycles at the forefront of discussions about existence and rebirth. A third hypothesis is the Big Rip, which speculates that dark energy, a mysterious force driving the universe's accelerated expansion, could grow stronger over time. In this case, the expansion would become so intense that it would tear galaxies apart, shatter stars, and ultimately disintegrate atoms themselves. This scenario paints a picture of a universe falling apart at the seams, with each layer of matter succumbing to increasing forces of distance. These theories not only provoke philosophical questions about existence, but also challenge our understanding of the fundamental forces shaping the cosmos. As researchers continue to explore the universe's mysteries, the true fate of our vast home remains one of the most profound questions in modern science. Each hypothesis carries significant implications for our understanding of time, space, and the very fabric of reality. Throughout history, various ancient civilizations have demonstrated an impressive understanding of astronomy through their technologies and constructions. For instance, the ancient Egyptians built the Great Pyramids of Giza with such precision that their alignment with the cardinal points of the compass is almost exact. They relied on meticulous observations of the stars to orchestrate the layout of these monumental structures, underscoring their advanced knowledge of celestial movements. Similarly, the ancient Mayans crafted an intricate calendar system that was remarkably accurate for its time. This calendar relied on the cycles of the sun, moon, and planets, with Mayan astronomers creating complex calculations to predict celestial events such as eclipses. They constructed massive observatories, such as those found in Uxmal and Chichen Itza, enabling them to track the positions of celestial bodies with astonishing precision. In Greece, the Antikythera mechanism stands out as a remarkable example of ancient technology. Discovered in a shipwreck off the coast of Antikythera, this ancient analog computer was designed to predict astronomical positions and eclipses for calendrical and astrological purposes. The complexity of its gears and sophisticated design reveal that the ancient Greeks possessed advanced engineering skills and a profound understanding of celestial mechanics. Another fascinating instance can be found in the megalithic structures of Stonehenge in England. This site, constructed around 5,000 years ago, exhibits astronomical alignments linked to the summer solstice and the lunar cycles. The placement of the stones suggests that those who built Stonehenge possessed both observational skills and a deep connection to the cosmos, allowing them to mark time and possibly conduct rituals centered around celestial events. These examples illustrate that advanced knowledge of astronomy was not the sole purview of modern science, but was evident in ancient civilizations throughout history. Scientists employ radio telescopes to probe the cosmos by capturing radio waves emitted by celestial objects. Unlike optical telescopes, which collect visible light, radio telescopes are designed to detect these invisible radio frequencies. Cosmic signals can provide insights into various phenomena, including pulsars, quasars, and even the cosmic microwave background radiation, remnants from the early universe. When a radio wave reaches Earth, the radio telescope's large dish collects and amplifies these signals. The signals are then translated into data that scientists can analyze. By studying the frequency, intensity, and timing of these waves, researchers can gain clues about the structure and behavior of the universe. For instance, the patterns of pulsar signals have educated scientists about the nature of gravity and even the behavior of space-time. One of the most captivating applications of radio telescopes has been the search for extraterrestrial intelligence. These instruments continuously scan the sky for unusual signals that are not easily attributable to natural cosmic phenomena. By using advanced algorithms and machine learning, scientists sift through vast amounts of data to identify potential signs of intelligent life. The infamous WOW signal recorded in 1977 remains a famous example of an unexplained radio signal that sparked curiosity and investigation. The effectiveness of radio telescopes lies in their ability to cover a wide range of frequencies, penetrating cosmic dust clouds and gas that often obscure visual observations. This multi-frequency approach to cosmic exploration provides an invaluable perspective on the universe, helping to unravel its mysteries while expanding our understanding of its origins and evolution. As science continues to evolve, the capabilities of radio telescopes will surely advance, opening new frontiers in our quest to understand the cosmos. Exploring the subsurface oceans of icy moons, such as Europa and Enceladus, has become a focal point in the search for extraterrestrial life and understanding the dynamics of our solar system. Advanced technologies are being developed that will allow scientists to penetrate ice shelves and analyze the ocean environments below. One exciting innovation is the use of autonomous underwater vehicles. These robots are designed to navigate the dark, cold waters beneath thick ice layers, equipped with sensors to gather data about temperature, salinity, and chemical composition. Another breakthrough lies in the development of ice-penetrating radar systems. These radar instruments can map the thickness of ice layers from orbit, allowing researchers to identify potential locations where subsurface oceans might be accessible. The data gathered can help select landing sites for future missions and guide the design of landers or drills capable of reaching the oceans hidden beneath the ice. Additionally, scientists are focusing on the design of specialized drill technologies that can melt through thick ice to access these watery environments. These drills would utilize small nuclear or thermal heating elements to create openings while minimizing contamination from Earth. Such careful planning is essential to maintain the integrity of these pristine ecosystems and to ensure valid scientific measurements. Lastly, orbiters are being equipped with sophisticated spectrometers to analyze the surface of these moons for signs of water vapor and other chemical indicators of subsurface oceans. By studying the plumes observed ejecting from Enceladus and the surface features of Europa, mission planners can gather vital clues about what lies beneath. This blend of technologies represents a bold step forward in our quest to understand not only the formation of these moons, but also the potential for life in these hidden alien oceans. The search for extraterrestrial intelligence, known as SETI, is a fascinating endeavor that combines the realms of technology and the quest for understanding our place in the universe. At the forefront of this search is a sophisticated array of technologies designed to detect signals from intelligent civilizations beyond our Earth. From radio telescopes to advanced signal processing software, each component plays a critical role in sifting through the vast sea of cosmic noise to locate potential messages from distant stars. One of the most prominent tools used by SETI is the radio telescope, particularly in facilities like the Arecibo Observatory or the Green Bank Telescope. These powerful instruments can capture radio waves across an extensive range of frequencies. Researchers honed in on the radio spectrum because many scientists believe that any advanced civilization would communicate over long distances using electromagnetic waves, much like our own methods of communication. By scanning the skies for unusual signals, SETI seeks to uncover anything that could hint at extraterrestrial life. Cutting-edge technology also extends to data analysis, where computer algorithms and artificial intelligence come into play. The sheer amount of data collected by radio telescopes can be staggering, often amounting to hundreds of terabytes every day. Advanced software is employed to filter out terrestrial noise, including signals from satellites and aircraft, allowing scientists to focus on more promising candidates. With machine learning techniques, these systems can improve over time, becoming increasingly adept at recognizing patterns that may indicate extraterrestrial origins. Moreover, SETI has embraced the power of crowdsourcing with initiatives like SETI at Home, which allows volunteers to use their personal computers to analyze radio signals when they are not in use. This innovative approach harnesses the computational power of thousands of individuals around the world, effectively creating a global network dedicated to the search for signs of extraterrestrial intelligence. As technology continues to evolve, so too does the potential to discover whether we are alone in the cosmos or if we share the universe with other intelligent beings. Artificial intelligence is becoming an indispensable tool in the exploration of cosmic mysteries. As astronomers sift through vast amounts of data from telescopes and space missions, traditional methods of analysis struggle to keep up with the sheer volume and complexity of information. Artificial intelligence algorithms can process this data at incredible speeds, identifying patterns and anomalies that human researchers might overlook. This capability opens up new avenues for discovering celestial phenomena, from exoplanets to the remnants of ancient stars. For instance, in the quest to detect exoplanets, artificial intelligence can analyze light curves from distant stars, looking for tiny dips in brightness caused by planets transiting in front of those stars. By employing machine learning techniques, these systems can improve their accuracy over time, becoming adept at distinguishing between genuine signals and noise. This approach has proven so effective that it has contributed to the identification of thousands of new exoplanets in our galaxy. Moreover, artificial intelligence is playing a crucial role in the study of gravitational waves. As events such as black hole mergers release ripples in space-time, artificial intelligence is used to recognize these fleeting signals within the noise of observational data. Advanced algorithms can hone in on the signatures of these cosmic events, helping scientists not only to detect them, but also to analyze their properties, ultimately leading to a deeper understanding of the universe's most violent processes. The potential of artificial intelligence does not end with analysis. It also extends to the design of new experiments and instruments. By simulating various cosmic scenarios, artificial intelligence can help researchers optimize observational strategies, ensuring that telescopes and instruments are focused on the most promising targets. This synergy between human ingenuity and machine learning represents a powerful collaboration, propelling the field of cosmology into new realms of discovery and understanding. Robotic missions have fundamentally transformed how we explore and understand our solar system, acting as our eyes and ears in the vast expanse of space. These incredible machines are capable of traveling to distant planets, moons, and asteroids, collecting data that would be impossible for humans to acquire in person. With technology that continually evolves, robotic spacecraft can withstand the harsh conditions of space, gathering valuable information about the origins and dynamics of our solar system. For instance, the Voyager spacecraft, launched in the late 1970s, has traveled farther than any other human-made object, sending back continuous data about the outer planets and eventually the interstellar medium. The insights gained from its journeys have reshaped our understanding of planetary atmospheres and magnetic fields. Furthermore, missions like the Mars rovers have unearthed evidence of past water flows, hinting at the possibility that our neighboring planet once had conditions suitable for life. Robots like the Juno spacecraft, currently orbiting Jupiter, have ventured near the gas giant to conduct in-depth studies of its composition and magnetosphere. This kind of exploration is crucial as it helps scientists piece together the history of planetary formation and evolution within our solar system. The information garnered informs not only our understanding of celestial bodies, but may also reveal the processes that govern planet formation universally. As missions continue to expand into uncharted territories, such as the New Horizons flyby of Pluto and beyond, we glean unprecedented knowledge about the outer realms of our solar system and even the Kuiper Belt. The ever-growing data collected by these robotic explorers empowers researchers to refine their models of celestial phenomena and unlock more secrets of our cosmic neighborhood. Through these missions, humanity gains a clearer and more comprehensive view of its place in the universe. Recent advancements in space-time mapping have come from a combination of theoretical physics and cutting-edge technology. Researchers have developed more sophisticated models that describe the curvature of space-time, influenced by massive objects like stars and black holes. Instruments such as laser interferometers are enabling scientists to detect gravitational waves. These ripples in space-time, first observed in 2015, provide clues into the energetic events occurring in the universe, revealing more about the fabric of space itself. The improvement of imaging techniques has also played a significant role. With the aid of radio telescopes and arrays that span vast distances on Earth, astronomers have been able to capture high-resolution images of phenomena at cosmic scales. This includes the Event Horizon Telescope's groundbreaking image of the black hole at the center of the Milky Way galaxy, which has allowed researchers to refine their models of how gravity influences space-time around such supermassive bodies. Each advancement in technology not only provides clearer images, but also deepens our understanding of theoretical frameworks. Despite these exciting developments, many mysteries remain within the realm of space-time. One of the biggest challenges is reconciling general relativity, which governs large-scale phenomena, with quantum mechanics, which operates at microscopic levels. This integration remains elusive, and scientists are searching for a unified theory that can successfully bridge these foundational pillars of physics. Moreover, the nature of dark matter and dark energy, which together make up approximately 95% of the universe, continues to baffle researchers as their effects on space-time are significant but not yet fully understood. Additionally, the concept of causality in relation to space-time raises intriguing questions. If space-time can be warped by extreme gravitational forces, what implications does this have for travel and communication across vast cosmic distances? These ongoing inquiries represent just a fraction of the vast intellectual landscape awaiting exploration, challenging humanity to look beyond the immediate and ponder the deepest workings of our universe. Gravitational lensing is a captivating phenomenon that occurs when massive objects like galaxies or clusters of galaxies bend the light from distant sources. This bending happens because the mass creates a gravitational field, which affects the trajectory of light traveling nearby. Astronomers have harnessed this effect as a valuable tool to study dark matter, an elusive component that makes up a significant portion of the universe's mass, but does not emit or interact with light in a way we can directly observe. When scientists observe a distant galaxy behind a massive object, they can see the light distorted into arcs or multiple images. This distortion provides a unique fingerprint of the mass distribution of the foreground object, allowing researchers to map out where the mass exists, even if it is primarily composed of dark matter. By analyzing these gravitational lensing effects, astronomers can infer the amount and distribution of dark matter in a given system, leading to insights about its role in the cosmic structure. One astonishing revelation from gravitational lensing studies is that dark matter does not cluster in the same way visible matter does. Instead, it forms a more diffuse halo around galaxies, influencing their motion and the formation of larger cosmic structures. This finding challenges our understanding of galaxy formation and evolution, suggesting a complex interplay between dark matter and visible matter that shapes the universe as we know it. Furthermore, gravitational lensing has led to discoveries of previously undetected structures in the universe. For instance, when scientists examined lensing effects from galaxy clusters, they uncovered hidden members of these clusters, revealing the true extent of dark matter's influence. Some studies even propose using future gravitational lensing surveys to probe the nature of dark matter itself, potentially uncovering new physics that could reshape our understanding of the universe. Through this lensing technique, the cosmic mystery of dark matter starts to become a little clearer, one distorted image at a time. Simulations play a crucial role in testing theories about the universe's early moments, essentially acting as virtual laboratories where physicists can model complex scenarios. These simulations allow scientists to recreate conditions thought to have existed shortly after the Big Bang, a pivotal moment when the universe began to expand from an extremely hot and dense state. By employing powerful algorithms and significant computational resources, researchers can examine how matter and energy would have interacted during that formative period. One primary application of these simulations is to investigate the formation of structures in the universe, such as galaxies and clusters of galaxies. The gravitational interactions that would have occurred in the dense plasma of the early universe can influence how matter coalesces to form the large-scale structures we observe today. By comparing simulated outcomes with observational data gathered from telescopes, scientists can refine their models and validate their theoretical predictions about cosmic evolution. Another aspect where simulations are invaluable is in the study of cosmic microwave background radiation. This faint afterglow from the Big Bang holds critical information about the universe's early conditions. Simulations provide insight into how fluctuations in density would have led to the anisotropies, or tiny temperature variations, seen in this radiation. By analyzing these variations, scientists can piece together details about the universe's expansion rate and the distribution of early matter. Moreover, simulations are essential for exploring the implications of various theoretical frameworks, such as inflation, which posits a rapid expansion of the universe in its earliest moments. As researchers develop and alter their models, simulations reveal how different scenarios might manifest in observable phenomena today, offering a pathway to test competing theories. Through such meticulous exploration, these computational tools illuminate our understanding of an era that remains largely enigmatic. Particle accelerators have revealed a treasure trove of insights about the universe, unlocking mysteries that lie at the very heart of matter and the fundamental forces that govern cosmic behavior. One of the most significant achievements has been the discovery of the Higgs boson, a particle that plays a crucial role in our understanding of mass. Identified for the first time in 2012 at the Large Hadron Collider, this elusive particle confirmed a critical aspect of the standard model of particle physics, explaining how particles acquire mass and ultimately shaping the structure of the universe we observe today. Beyond discovering the Higgs boson, particle accelerators experiment with conditions similar to those moments after the Big Bang, allowing scientists to study matter at temperatures and energies that existed when the universe was merely a few moments old. These experiments provide insights into the behavior of quarks and gluons, the very building blocks of protons and neutrons. By smashing particles at near light speeds, researchers observe interactions that can shed light on phenomena such as dark matter and antimatter, two of the universe's greatest puzzles. Furthermore, particle accelerators aid in exploring beyond the visible spectrum of matter. They provide experimental evidence to test theories such as supersymmetry, which posits the existence of partners for known particles, potentially offering solutions to several unresolved problems in theoretical physics. By pushing the boundaries of our existing models, these accelerators challenge our understanding and occasionally hint at new physics, igniting curiosity and extending the frontiers of knowledge. In addition, advancements in technology arising from particle physics research have far-reaching applications beyond the accelerator walls. Techniques developed for particle detection have been adapted for medical imaging and cancer treatments, demonstrating the practical impacts of understanding the universe's microcosm. This interplay between high-energy physics and everyday technology continues to bear fruit, showcasing the profound connection between exploring the cosmos and improving life on Earth. Mars has long captivated scientists and space enthusiasts alike, largely due to its potential to have once harbored life. Among the most compelling discoveries are the signs of ancient water, fundamental to life as we know it. In recent years, rovers like Curiosity and Perseverance have unveiled evidence of river deltas, lake beds, and mineral formations that typically form in the presence of water. These geological features suggest that liquid water existed on the Martian surface for long periods, offering a hospitable environment for microorganisms. Additionally, researchers have found carbonates and sulfates embedded in rocks and soil, substances often associated with biological processes on Earth. The presence of these minerals indicates that water not only existed, but was also chemically active, creating conditions similar to those where life began on our planet. Furthermore, studies of Martian meteorites found on Earth have revealed organic molecules, which are the building blocks of life. These molecules raise intriguing questions about the possibility of ancient microorganisms on Mars. In recent missions, scientists have also detected methane in the Martian atmosphere. While this gas can result from geological processes, it is frequently produced by living organisms on Earth. The cycles of methane on Mars hint at ongoing processes, whether biotic or abiotic, that warrant further investigation. Each piece of evidence adds to a growing tapestry of discoveries that increase the likelihood that Mars was once home to microbial life forms. With each rover mission and analytical study, we move closer to answering the question of life beyond Earth. The tantalizing possibilities raised by these discoveries encourage ongoing exploration and research, pushing humanity's quest for knowledge deeper into the cosmos. Determining the habitability of planets beyond our solar system, known as exoplanets, involves a multifaceted approach that combines astronomy, planetary science, and even biology. Scientists first assess key factors, such as the planet's location within the so-called habitable zone. This region is where conditions are just right for liquid water to exist on a planet's surface, a crucial ingredient for life as we know it. If a planet is too close to its star, it might be scorching hot, whereas if it is too far away, it could be frozen over. Next, researchers consider the planet's atmosphere. An atmosphere can protect a planet from harmful radiation and help regulate temperature. To evaluate an exoplanet's atmosphere, scientists use spectroscopy, a technique that analyzes the light spectrum from the planet. By studying how starlight changes when it passes through a planet's atmosphere, scientists can identify the presence of gases like oxygen, carbon dioxide, and methane, which are potential indicators of biological activity. Scientists also investigate the planet's composition and geological features. A rocky planet with a solid surface is typically more likely to support life than a gaseous giant. Factors such as the presence of minerals that can provide essential nutrients, volcanic activity that can create nutrient-rich environments, or even the stability of the planet's climate over long periods are all critical aspects of habitability. The presence of a magnetic field can also be important, as it shields a planet from harmful solar radiation, which could damage potential biological systems. All these factors come together to paint a picture of whether a distant world might support life. The exploration of exoplanets is still in its infancy, but as technology advances, researchers are uncovering more about these distant places. Each new discovery brings us closer to understanding not just where life can exist, but also the unique conditions that might allow it to thrive on other worlds. Extremophiles are remarkable organisms that thrive in some of the most hostile environments on Earth, where most life forms cannot survive. These resilient beings can withstand extreme temperatures, high radiation levels, acidic or alkaline conditions, and intense pressures. They have become a focal point in the search for extraterrestrial life, as their existence suggests that life could flourish in environments previously deemed uninhabitable. The study of extremophiles has revealed the versatility of life and its ability to adapt. For instance, microorganisms found in the deep ocean vents where superheated water erupts from the Earth's crust utilize chemosynthesis instead of photosynthesis. This adaptation enables them to derive energy from chemical reactions rather than sunlight, a process that could be vital in similar alien settings. Discoveries like these extend our understanding of the conditions under which life can arise and persist, expanding the search for life beyond our planet. In addition to proving that life can exist in extreme conditions, extremophiles serve as useful models for astrobiology, the study of life in the universe. By simulating extraterrestrial environments, researchers can use extremophiles to develop tests and missions aimed at finding life on other planets or moons. For example, the icy subsurfaces of Jupiter's moon Europa or Saturn's moon Enceladus may harbor conditions analogous to those extremophiles navigate here on Earth, hinting at the potential for life beyond our atmosphere. Overall, extremophiles not only enhance our understanding of life's adaptability, but also stimulate our imagination about the possibilities of life in the universe. Their inherent resilience inspires scientists to explore the farthest reaches of space in the search for alien life, reinforcing the idea that if life can exist in Earth's extreme environments, it may endure elsewhere in the cosmos as well. Europa, one of Jupiter's largest moons, presents intriguing conditions that hint at the possibility of life. Beneath its icy surface lies a vast ocean of liquid water, which may be in contact with a rocky seabed. This interaction could create a rich environment, much like what we find in Earth's deep-sea hydrothermal vents, where unique life forms thrive in complete darkness, nourished by mineral-laden water. The presence of water is essential for life as we know it, serving as a solvent for biochemical reactions. The oceans on Europa are believed to be kept warm through tidal heating, generated by the gravitational pull of Jupiter and the other Galilean moons. This process can maintain temperatures that prevent the ocean from freezing solid, providing a stable environment where life could potentially develop. Moreover, the icy shell covering Europa can also provide protection from harsh radiation and extreme temperatures in outer space. This icy layer may act as a shield, allowing life to evolve in the more hospitable conditions beneath. Scientists theorize that this subsurface ocean could contain the basic ingredients for life, such as organic molecules and nutrients, essential for various biochemical processes. Intriguingly, future missions to Europa may focus on exploring its ocean and searching for signs of life. By analyzing the plume eruptions spotted by spacecraft, researchers hope to obtain samples directly from the Moon's subsurface ocean. This ambitious exploration could elevate our understanding of where and how life might exist beyond Earth, making Europa a prime candidate in the ongoing search for extraterrestrial life. Meteorites have become remarkable messengers from the cosmos, offering tantalizing clues about the possibility of life on other worlds. Since the dawn of human curiosity about the universe, these ancient space rocks have inspired speculation regarding the building blocks of life beyond Earth. When we study meteorites, we find that some contain organic compounds, which are the fundamental ingredients for life as we know it. One renowned group of meteorites, known as carbonaceous chondrites, is particularly significant in this quest. These meteorites include amino acids, the building blocks of proteins, which suggest that the chemistry necessary for life might be more widespread in the universe than previously thought. These findings lead scientists to consider that the essential components for life may have formed in space and could potentially be delivered to planets during their formative years. Moreover, certain meteorites originate from Mars, giving us direct insight into our neighboring planet's past. Some of these Martian meteorites contain signs of microbial life, or at the very least, the right conditions that could have supported life. The presence of features resembling fossilized organisms has sparked intense interest and debate, highlighting the notion that Mars may have once harbored life. These discoveries deepen our understanding of life's origins. They raise profound questions about whether life could emerge independently elsewhere in the universe, potentially existing on other celestial bodies where conditions allow for such chemistry to flourish. Each meteorite unearthed opens a new window into this ongoing exploration, confirming that the universe holds both mystery and potential. Panspermia is a fascinating concept that suggests life may not be restricted to just one planet, but could instead travel across the cosmos. This theory postulates that microscopic life forms, such as bacteria or spores, can survive the extreme conditions of space. These tiny organisms can potentially hitch a ride on meteoroids, comets, or even interstellar dust particles. When these celestial bodies collide with planets, they might deliver their precious cargo of life. Through this process, astrobiologists theorize that life could initiate on one planet and be transported to another, seeding new worlds with the building blocks of biology. The discovery of extremophiles, organisms that thrive in conditions previously thought impossible for life, bolsters this idea. Such microorganisms have demonstrated resilience against high radiation, intense heat, and extreme cold, suggesting they could endure the harsh journey through space, protected within a rock or ice. Further intrigue emerges with the realization that ancient meteor impacts may have supplied Earth with vital organic materials. This possibility raises questions about our own origins and the interconnectedness of life across the universe. Some researchers even speculate about the potential for complex life to travel this way, igniting debates about the cosmic origins of species and the potential for extraterrestrial life influencing evolution on Earth. Additionally, some experiments have already shown that certain life forms can survive exposure to the vacuum of space and cosmic radiation. These findings open rich avenues for exploration, suggesting that life may be more resilient and widespread than previously imagined. The implications of panspermia extend beyond simple survival. They challenge our understanding of biology and the very nature of life itself as a cosmic phenomenon. The Drake equation serves as a fascinating framework in our quest to understand the potential for extraterrestrial life in the cosmos. This equation, proposed by the astronomer Frank Drake in 1961, attempts to estimate the number of civilizations within our galaxy with which we might be able to communicate. It takes into account various factors, such as the rate of star formation, the fraction of those stars that have planets, and the likelihood of life developing on those planets. One significant implication of the Drake equation is that it highlights how many variables contribute to the emergence of intelligent life. Each term in the equation represents uncertainties that scientists are eager to explore. The more we learn about exoplanets, planets outside our solar system, the better we can refine our estimates. Discoveries such as the thousands of confirmed exoplanets and the identification of potentially habitable zones around their parent stars have fueled optimism about the existence of other life forms. Additionally, the Drake equation prompts us to think critically about what constitutes life. The factors included in the equation tend to focus on carbon-based Earth-like scenarios. This encourages astrobiologists to broaden their definitions and consider life forms that might thrive in completely different environments, perhaps biochemically distinct from our own. This expanded perspective enhances our search and fosters collaboration among scientists from various disciplines, each contributing insights that could bridge gaps in our understanding. Moreover, the equation underscores the importance of technological development and global collaboration in searching for extraterrestrial signals. As our tools and techniques improve, so too does our ability to scan the vast skies for signs of life. This quest is not just about discovering intelligent civilizations, it also fuels questions about our own existence and our place in the universe. As we refine these estimates, the exploration of life beyond our planet continues to engage and inspire, reminding us that we are part of a much larger cosmic story. Scientists harness the principles of biochemistry to create models of alien ecosystems by analyzing the basic building blocks of life as we understand it here on Earth. They begin by identifying biosignatures, which are indicators of life such as specific molecules or chemical patterns that arise from living organisms. Through exploring the biochemical functions of various life forms on our planet, researchers extrapolate these findings to hypothesize about what alien biochemistry might look like. By studying extremophiles, organisms that thrive in extreme conditions, scientists gain valuable insights into the resilience and adaptability of life. These organisms demonstrate that life can exist in environments previously deemed inhospitable, such as boiling hot springs or deep-sea hydrothermal vents. Such discoveries fuel the imagination of researchers, allowing them to propose that alien life forms may also employ a different set of biochemical processes to survive similar harsh environments on other planets or moons. Additionally, computer simulations play a critical role in this exploration. Researchers input data about known biochemical processes and conditional variables, creating intricate models that reveal how life might thrive in diverse alien ecosystems. For instance, they consider factors such as temperature, atmospheric composition, and radiation levels, predicting how organisms might adapt over time. Such models help clarify the potential interactions between different life forms and their environments, giving a clearer picture of possible alien life. Crucially, scientists also factor in the role of carbon and other elements in the formation of life. While carbon is central to terrestrial life due to its versatile bonding properties, researchers consider other elements like silicon as potential alternatives for biochemistry. This broadens the possibilities for life and ecosystems beyond Earth, suggesting that by understanding biochemistry, we can push the boundaries of what life could be in the cosmos. Research into exoplanets, or planets beyond our solar system, has revealed astonishing insights that deepen our understanding of where intelligent life might exist. The discovery of these celestial bodies began earnestly in the mid-1990s, and as technology has advanced, scientists have identified thousands of exoplanets, some of which reside in a zone known as the habitable zone. This region around a star is where conditions may be just right for liquid water to exist on the surface, a critical factor in the search for life. One of the most promising exoplanets discovered in this search is named Kepler 186f. This Earth-sized planet orbits its star within the habitable zone, receiving a similar amount of sunlight as Earth does from the Sun. Its size and distance from its star suggest that it could potentially maintain liquid water. Researchers have also identified exoplanets like Proxima Centauri b, which orbits the closest star to our Sun. Although its conditions remain uncertain, the mere proximity of this planet makes it a compelling candidate for further study regarding the possibility of life. Beyond simply existing in the habitable zone, the characteristics of a planet's atmosphere play a significant role in assessing its potential to support life. For instance, the detection of gases like oxygen, methane, and carbon dioxide through spectrometry hints at biological processes similar to those on Earth. The James Webb Space Telescope, launched recently, has enhanced our ability to study these atmospheres and analyze their compositions, which could reveal whether the necessary ingredients for life are present. These discoveries ignite the imagination and fuel the questions we have about our place in the universe. By continuing to analyze exoplanets and their atmospheres, scientists move closer to answering whether we are alone in this vast cosmos. The tantalizing thought that intelligent life could exist elsewhere not only motivates exploration, but also underscores the intricate balance required for life as we know it to thrive. Obscure oceanic organisms on Earth provide fascinating insights into the potential for life beyond our planet. Found in extreme environments, these remarkable creatures thrive in places where most life would struggle to survive, such as hydrothermal vents deep in the ocean and frigid polar regions. By studying these organisms, scientists glean crucial information about the conditions that can support life, even in the most inhospitable environments. One of the most compelling examples includes extremophiles, which are organisms that endure severe temperatures, high pressures, or extreme acidity. Among them are tube worms that live near hydrothermal vents, utilizing chemosynthesis instead of photosynthesis to convert energy from chemicals spewing from the Earth's crust into sustenance. This adaptability suggests that life can arise in different forms, utilizing varying energy sources, which could inform our search for extraterrestrial life on moons like Europa or Enceladus, where subsurface oceans exist beneath icy surfaces. Additionally, the diverse array of genetic and physiological traits evident in these oceanic organisms can provide models for understanding how life might evolve under varying extraterrestrial conditions. By examining the genetic adaptations that allow these organisms to withstand their harsh environments, Scientists can formulate hypotheses about potential alien life forms and their possible adaptations to non-Earth-like climates or chemical compositions. Furthermore, the discovery of unique biochemical pathways in these organisms has implications for astrobiology, the study of the potential for life elsewhere in the universe. As missions probe the icy surfaces of other celestial bodies, the understanding garnered from these earthly organisms serves as a guide, directing researchers in their quest to answer age-old questions about life beyond our home planet, expanding the horizons of both evolutionary biology and the search for extraterrestrial intelligence. Cosmology, the study of the universe at the grandest scale, is rich with mysteries that persist despite decades of research and discovery. One significant unsolved problem is the nature of dark matter. This enigmatic substance makes up approximately 27% of the universe, yet it has yet to be directly detected. Although scientists have inferred its existence from gravitational effects, such as the way galaxies rotate and how light bends around massive objects, the actual particles that constitute dark matter remain elusive. Another major puzzle is dark energy, which is thought to account for about 73% of the universe's total energy content. This mysterious force is responsible for the accelerated expansion of the universe, a phenomenon that was first observed in the late 20th century. Researchers have yet to fully understand what dark energy is or why it has such a profound effect on the cosmos. Various theories abound, but a definitive answer remains out of reach. Cosmic microwave background radiation, a residual afterglow from the Big Bang, presents another area of intrigue. While we have captured detailed images of this cosmic relic, questions remain regarding its uniformity and any anomalies that could suggest other dimensions or aspects of the universe not yet understood. The slight fluctuations we observe in the cosmic microwave background hold clues to the early universe, but deciphering these remains a challenge. Lastly, the concept of the multiverse captivates scientists as well as the public's imagination. Some theories suggest that our universe is just one of many, with each existing in its own bubble of space-time. If this multiverse hypothesis is accurate, it could fundamentally alter our understanding of reality. Nevertheless, testing the existence of parallel universes remains a formidable task, leaving cosmologists eager for future breakthroughs that could unlock these enduring mysteries. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and their origins continue to puzzle scientists. The majority of these particles come from outside our solar system, with some even believed to originate from distant galaxies. Among their sources we find supernovae, where massive stars explode at the end of their life cycles, creating shockwaves that accelerate particles to extraordinary velocities. Other potential origins include active galactic nuclei and neutron stars, which are incredibly dense and can emit energetic particles due to their intense magnetic fields. One of the most compelling mysteries surrounding cosmic rays is their composition. While they mostly consist of protons, a significant portion includes heavier atomic nuclei and even electrons. Scientists have long sought to understand how such a diverse array of particles can reach such high energies. The discussion around ultra-high-energy cosmic rays is particularly intriguing. These particles possess energies beyond what current models of particle physics can readily explain, leading to a multitude of questions about their origin and the processes that give rise to such astonishing energies. Another captivating aspect of cosmic rays is how they interact with the Earth's atmosphere. When they collide with air molecules, they produce showers of secondary particles that cascade down to the surface. This process opens the door to studying cosmic rays using ground-based detectors. The nature of these secondary particles provides researchers with valuable insights into the properties of cosmic rays and their sources, adding layers of understanding to this enigmatic phenomenon. Understanding cosmic rays not only sheds light on their origins, but also helps scientists probe deeper into the fundamental processes of our universe. Each discovery about cosmic rays leads to new questions, making the study of these high-energy particles a compelling field that intersects with astrophysics, particle physics, and cosmology. As we continue to explore the mysteries surrounding cosmic rays, we inch closer to unraveling the secrets of the cosmos itself. The Fermi paradox stands as a pivotal concept in our exploration of extraterrestrial life. Named after the renowned physicist Enrico Fermi, the paradox juxtaposes the high probability of extraterrestrial civilizations existing somewhere in the universe with the glaring lack of evidence for or contact with such civilizations. The universe is vast, containing billions of galaxies and countless stars, many of which likely host planets in the habitable zone where life could potentially thrive. Given these staggering numbers, one would expect to see signs of intelligent life. Yet despite extensive searching, we find ourselves seemingly alone in this cosmic expanse. One of the key points that arise from the Fermi paradox is the challenge of technological advancement and longevity. It invites us to ponder whether intelligent civilizations inevitably self-destruct before they can venture into the stars or communicate across the vast emptiness of space. History provides us with a sobering perspective. Earth itself has witnessed numerous civilizations rise and fall, suggesting that perhaps the development of advanced civilization is a precarious journey fraught with existential risks. Finally, the Fermi paradox highlights our own place within this grand cosmic theater. It urges us to reflect on the sustainability of our civilization and the importance of safeguarding our planet. As we gaze into the night sky, we are not merely seeking companions among the stars. We are challenged to maintain our own existence and learn what it means to be a responsible player in a universe brimming with possibility yet shrouded in mystery. Pulsars are fascinating astronomical objects that function much like cosmic lighthouses, emitting beams of radiation that sweep across space as they rotate. These highly magnetized, rotating neutron stars emit electromagnetic radiation in the radio, visible, and even gamma-ray wavelengths. As a pulsar spins, its lighthouse beam is only visible from certain angles, similar to how the light from a lighthouse is only seen from specific positions along the shore. When Earth aligns with this rotating beam, observers on our planet detect regular pulses of radiation, often occurring with remarkable precision. The rapid rotation of pulsars, which can complete a single rotation in mere milliseconds, leads to these consistent pulses that scientists can measure with extraordinary accuracy. This quality allows astronomers to use pulsars as cosmic clocks, providing a stable reference for measuring time and aiding in navigation across deep space. The repetitive nature of their emissions makes it possible to study gravitational waves, test theories of relativity, and even investigate the inevitable fate of neutron stars themselves. Beyond their role in cosmic navigation, pulsars hide a wealth of secrets regarding the extreme conditions of their formation. When massive stars undergo supernova explosions, they leave behind these incredibly dense remnants. A teaspoon of pulsar material could weigh as much as a mountain on Earth, showcasing the exotic physics at play in their interiors. Researchers strive to understand the behavior of matter in such extreme environments, which could shed light on fundamental questions related to particle physics and the state of matter at high densities. The intricate dynamics of pulsars also expose the mysteries of the cosmos, including insights into the interstellar medium and the conditions that lead to their formation. Studying these unique celestial objects grants astronomers the opportunity to unlock the history of our universe, revealing details that stretch back billions of years. Each pulse of a pulsar offers a glimpse into the nature of space, time, and the fundamental forces that govern our reality. The anomalous motions of certain celestial bodies challenge our understanding of gravitational dynamics and the forces at play within our universe. Observations have revealed peculiar trajectories that cannot be fully explained by the known laws of physics, prompting scientists to seek explanations beyond the conventional. These irregularities often suggest the presence of unseen mass, leading to theories about dark matter, an elusive form of matter that does not emit light or energy in detectable ways. For instance, when astronomers analyze the rotation curves of galaxies, they notice that stars at the outer edges rotate at speeds that defy predictions based on the observable mass of the galaxy. This discrepancy implies that there must be additional mass influencing their motion, even if that mass cannot be seen. This has led to the hypothesis that dark matter constitutes a significant portion of the universe, shaping the structure of galaxies and galaxy clusters with its gravitational pull. Moreover, anomalies in the orbits of certain celestial objects, like the dwarf planet Eris or the hypothesized planet 9, further indicate that there could be substantial gravitational influences at play, potentially hinting at large, undiscovered planetary bodies located in the far reaches of our solar system. Such hypotheses invigorate astronomical research, inspiring new missions and studies to explore these celestial oddities and uncover deeper truths about our cosmic neighborhood. The implications of these findings extend beyond just the dynamics of celestial bodies. They touch on fundamental questions about the composition of the universe and the laws governing it. As scientists investigate these anomalies, they continue to refine our understanding of gravity, matter, and the very fabric of the cosmos. Each discovery brings us one step closer to understanding the unseen forces that shape the universe we inhabit. The discovery of fast radio bursts has introduced a fascinating new mystery to the field of astrophysics. These powerful millisecond-long pulses of radio waves originate from distant galaxies and were first detected in the year 2007. Initially, scientists struggled to explain their origins, leading to numerous theories ranging from cosmic phenomena to potential extraterrestrial signals. This uncertainty pushes the boundaries of what we understand about the universe. Fast radio bursts challenge pre-existing notions by demonstrating that there are cosmic events capable of releasing enormous amounts of energy in a remarkably brief amount of time, far exceeding traditional models of astrophysical phenomena. Observations show that these bursts can outshine entire galaxies, leaving scientists to ponder the astrophysical processes involved in their creation. The ability of these bursts to convey clues about the environment they travel through also enhances our understanding of intergalactic space and the matter that exists there. One of the most compelling aspects of fast radio bursts is their sporadic nature. Each event seems to occur randomly, making them difficult to predict and study in detail. This unpredictability raises questions about the underlying mechanisms driving these bursts. Some researchers propose that they could be linked to phenomena such as neutron star collisions or magnetars, which are highly magnetized neutron stars. Investigating these possibilities requires careful observation and theoretical evolution, pushing scientists to reevaluate and expand their models of cosmic phenomena. As researchers continue to analyze and classify these enigmatic signals, the field of astrophysics stands at the brink of significant advancements. The compelling nature of fast radio bursts invites not only further exploration, but also a rethinking of what we know about the universe, ultimately opening new pathways for scientific inquiry and discovery. The hunt for dark galaxies, those mysterious structures that may lack the bright stars typically seen in their brighter counterparts, has captivated astronomers for years. The evidence suggesting their existence primarily stems from observations of gravitational effects in regions of space where visible matter seems insufficient. For instance, when studying certain areas of the universe, researchers have detected peculiar movements of gas and stars that don't align with the amount of visible matter present. This inconsistency indicates that there must be additional unseen mass at play, which provides a strong hint toward the presence of dark galaxies. Astronomers often rely on techniques like gravitational lensing to piece together the puzzle of dark galaxies. When light from a distant source, such as a quasar, passes near a massive object, it bends around it, creating a magnified or distorted image. By examining these distortions, scientists can infer the presence of additional mass, even when it is not directly observable. Dark galaxies are thought to contain significant amounts of this unseen dark matter, which contributes to their gravitational influence without emitting light. Additionally, observations using radio telescopes have revealed cold gas clouds that do not correspond to any visible galaxy. These clouds, which are often rich in hydrogen, support the hypothesis that they are remnants of galaxy formation that have not yet developed into star-producing entities. The existence of these cold gas clouds further suggests a population of galaxies that exist predominantly in the dark matter state, where their potential for star formation is hindered or simply has not yet occurred. By piecing together these various strands of evidence, astronomers build a picture of a universe that may be more complex than originally conceived. The dark galaxies, sitting quietly in the expansive cosmos, challenge our understanding of galaxy formation and evolution. As researchers continue to refine their techniques and technologies, the quest to uncover the secrets of these elusive structures deepens, promising exciting discoveries and insights about the fundamental nature of our universe. Saturn's rings captivate the imagination not just because of their stunning beauty, but also due to the scientific mysteries they present. These rings, comprising ice particles, rocky debris, and dust, have intrigued astronomers for centuries. One of the most profound questions surrounding them is their formation. While many theories suggest that they may have originated from a moon that was torn apart by Saturn's gravitational pull, the exact events that led to the creation of the rings remain elusive. Another mystery lies in the age of these rings. While Saturn itself has existed for over 4 billion years, some researchers propose that the rings may be much younger, possibly formed as recently as a few 100 million years ago. This difference in ages leads to intriguing discussions about their longevity and what this means for the history of the Saturnian system. If the rings are indeed relatively young, they offer a unique window into the dynamic processes of the solar system, revealing how celestial bodies can evolve over time. Furthermore, studying the rings contributes to our understanding of fundamental physics. The structure of the rings, featuring sharp edges and gaps, poses questions about the gravitational interactions at play. These phenomena suggest the presence of tiny moonlets within the rings that influence the distribution of material, showcasing the complex dance of gravity and motion. This aspect of the rings invites researchers to explore the intricate relationships between celestial mechanics and the formation of planetary ring systems. Saturn's rings also serve as a laboratory for planetary science, allowing scientists to investigate broader cosmic phenomena. The interactions between the rings and Saturn's many moons create a rich environment for understanding how celestial bodies interact with one another. This ongoing research not only deepens our knowledge about Saturn, but also provides insights into the nature of ring systems beyond our own planet. The mysteries of Saturn's rings continue to expand our understanding of the universe, encouraging curiosity about the forces that shape our celestial neighborhood. The enigma, commonly referred to as the Great Silence of the Universe, raises profound questions about extraterrestrial life. Despite the vastness of the cosmos, with billions of galaxies and countless stars that likely host potentially habitable planets, we have yet to find definitive evidence of intelligent life beyond our planet. Various theories attempt to illuminate why we seem so alone in the universe. One prominent theory is the Fermi paradox, which examines the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of contact with any such civilizations. The paradoxes suggest that either intelligent life is exceedingly rare, or perhaps civilizations tend to self-destruct before they can establish interstellar communication. Factors such as nuclear war, climate catastrophe, or uncontrolled technological advancements might contribute to this phenomenon. Another consideration involves the technological capabilities needed for advanced civilizations to communicate across the vast expanses of space. It is possible that such civilizations exist, but are using communication methods beyond our current understanding or capabilities. They may also not be using radio waves, which is the primary medium we search for. Additionally, the great distances involved mean that signals take a very long time to traverse space, leading to the chance that we may be missing signals that are very old by the time they reach us. The notion of the Great Filter further complicates this mystery. This concept postulates that at some stage in the evolution of life, a significant barrier or filter exists that most civilizations fail to surpass. This filter could lie ahead of us in our future, suggesting that humanity faces potential extinction from various cosmic or self-inflicted threats. Alternatively, the Great Filter could have occurred in our past, implying that while many planets may have birthed life, very few have ever progressed to the stages of technological advancement necessary for interstellar communication. Each of these theories adds depth to our understanding of why the universe remains silent, sparking not only scientific inquiry, but also philosophical reflection. The cosmic web structure reveals a fascinating tapestry that hints at the universe's evolution over billions of years. It is a framework of galaxies, gas, and dark matter interconnected by vast filaments, forming a web-like arrangement. This intricate structure is not merely random, rather, it offers a glimpse into the forces that have shaped our universe since its inception. Primarily, the cosmic web is thought to have its roots in the tiny fluctuations of density that occurred shortly after the Big Bang. These small variations in density allowed gravity to play an essential role, pulling matter together and leading to the formation of massive structures. As time progressed, regions of higher density attracted more matter, resulting in clusters of galaxies and enormous voids where fewer galaxies are found. This ongoing process of gravitational attraction suggests a dynamic evolution, continuously molding the universe we observe today. In addition to highlighting gravity's role, the cosmic web illustrates how dark matter influences structure formation. Though invisible and undetectable through conventional means, dark matter constitutes a significant portion of the universe's mass and is thought to be mainly responsible for the web's shape. This phenomenon emphasizes the tandem dance of visible and invisible forces at play in the cosmos. Studies of the cosmic web, such as through advanced simulations and observations from telescopes, provide evidence that supports our understanding of cosmic evolution. Collectively, these structures not only depict the universe's past, but also inform predictions about its future. As galaxies continue to move and evolve within this web, they may collide, merge, or drift apart, influencing their growth and behavior. This ongoing cosmic evolution reveals the complex interplay of forces that have shaped the universe and continues to drive its future trajectory. Throughout history, several ancient civilizations laid the groundwork for our understanding of the stars and celestial movements. The Babylonians are often recognized for their significant contributions, as they meticulously observed the night sky and recorded celestial events on clay tablets. Their calculations of planetary positions and lunar phases enabled them to develop an early form of astronomy that would influence future civilizations. Meanwhile, the ancient Egyptians also played a crucial role in astronomical advancements. The construction of their pyramids was aligned with the stars, particularly with Sirius and Orion, reflecting their deep understanding of the heavens. Egyptian astronomers tracked the annual flooding of the Nile River by observing the heliacal rising of Sirius, which was critical for agricultural planning and daily life. In Mesoamerica, the Maya civilization made extraordinary contributions to astronomy, creating complex calendars based on their observations of celestial bodies. They developed sophisticated techniques for predicting solar and lunar eclipses and meticulously recorded the movements of planets. Their knowledge of astronomy was so advanced that it was often interwoven with their religious beliefs, highlighting the intrinsic connection between their cultural practices and the cosmos. The Greeks further enriched astronomical knowledge, building upon the observations of earlier civilizations. Notably, figures like Ptolemy and Aristotle made significant advancements, introducing theories about the geocentric model where the Earth was thought to be at the center of the universe. This model dominated for centuries before being challenged by later discoveries. Each civilization, in unique ways, paved paths of understanding that continue to resonate in modern astronomy. Early astronomers laid the groundwork for our understanding of the universe long before the advent of modern technology. They relied on keen observation, meticulous record-keeping, and rigorous reasoning to develop their models. Night after night, these pioneers of astronomy would gaze at the stars, noting their positions and movements against the celestial sphere. With no telescopes or advanced instruments, they used only their eyes, but their focused attention allowed them to detect patterns and cycles in the heavens. One of the most significant contributions came from ancient civilizations such as the Babylonians, Egyptians, and Greeks. They created basic models of the cosmos that shaped our understanding for centuries. For instance, the Greeks proposed a geocentric model, placing Earth at the center of the universe, surrounded by celestial spheres that held the moon, sun, and stars. The philosopher Claudius Ptolemy developed this idea further in the 2nd century, emphasizing that the cosmos was orderly and predictable, a notion that echoed throughout the Middle Ages. These astronomers also utilized geometry when constructing their celestial models. They observed phenomena such as the phases of the moon and the apparent retrograde motion of planets. By employing mathematical principles and reasoning, they sought to explain these observations. The use of simple tools, such as the gnomon, a vertical stick that casts a shadow, allowed them to measure the sun's position at different times, aiding their understanding of solar cycles and timekeeping. Despite their lack of sophisticated instruments, their dedication to observation and logical reasoning laid the foundation for later, more advanced explorations of the universe. Their work paved the way for thinkers like Nicolaus Copernicus and Galileo Galilei, who would ultimately challenge the long-held beliefs of their predecessors and move us toward the heliocentric model, marking a significant shift in our perception of the cosmos. The invention of the telescope was a monumental leap in humanity's ability to understand the universe. Before its advent, our view of the cosmos relied heavily on the naked eye, limiting our understanding to what could be seen from Earth. The telescope, first developed in the early 17th century, allowed astronomers to observe celestial objects in unprecedented detail, fundamentally changing our comprehension of the universe and our place within it. Galileo Galilei, one of the earliest adopters of this remarkable instrument, utilized the telescope to make groundbreaking observations. He revealed the moons of Jupiter, showcasing that not all celestial bodies revolve around the Earth, a finding that challenged the geocentric model that had dominated for centuries. His discovery of sunspots and the detailed phases of Venus further supported the heliocentric model, ultimately reshaping the entire landscape of astronomy and physics. The impact of the telescope did not end with Galileo. Subsequent advancements, like Isaac Newton's reflecting telescope, provided even clearer views of the cosmos. Observatories equipped with telescopes became crucial in the pursuit of knowledge, enabling astronomers to catalogue countless stars, nebulae, and galaxies. This accumulation of data paved the way for the formulation of new theories about the structure and evolution of the universe, such as the realization that the Milky Way is a spiral galaxy, one of millions in a vast cosmos. As technology continued to evolve, so did the capabilities of telescopes. The development of radio telescopes expanded our reach even further, allowing us to study cosmic phenomena that emit radio waves rather than visible light. With instruments located in space like the Hubble Space Telescope, we are now able to observe the universe without the interference of Earth's atmosphere. Each advancement unfolds new layers of knowledge, continually transforming our cosmic perspective and revealing the complex tapestry of the universe we inhabit. The Copernican revolution marked a profound turning point in how humanity perceives its place in the universe. Before this revolution, the prevailing belief was that Earth occupied a central position in the cosmos, a view known as geocentrism, which had been held since ancient times. The model positioned Earth at the center, with the sun, moon, and stars revolving around it. This perspective instilled a sense of importance and uniqueness to our planet, and gave humanity the illusion of being at the forefront of the universe. When Nicolaus Copernicus introduced his heliocentric model in the 16th century, everything changed. By proposing that the sun, rather than the Earth, was at the center of the universe, he shifted the framework of cosmic understanding. This radical idea diminished the perceived significance of Earth and humanity within the grand scheme of things. Instead of being the focal point of creation, we became just one of many celestial bodies orbiting a larger entity. The sun was no longer a mere fixture in the heavens, but the center around which everything revolved, suggesting a more dynamic, chaotic, and interconnected universe. This shift had far-reaching implications, not only in the realm of science, but also in philosophy and religion. As the heliocentric model gained traction, it challenged long-standing doctrines that placed humanity at the center of the divine order. Individuals began to question their special status in the universe, leading to a gradual re-evaluation of man's relationship with nature and the cosmos. The sense of grandiosity that once enveloped humanity began to fade, replaced by a humbler recognition of our place in an expansive universe filled with countless stars and planets. Moreover, the Copernican revolution laid the groundwork for future scientific inquiry and discoveries. It encouraged a new way of thinking, emphasizing observation and reason over established tradition. This shift paved the way for the works of subsequent astronomers like Galileo Galilei and Johannes Kepler, whose contributions continued to unravel the mysteries of the cosmos. Ultimately, the Copernican revolution invited humanity to ponder deeper questions about existence, our roles in the universe, and the nature of reality itself. It reshaped our understanding of the cosmos, making it clear that we are but a small part of a vast and ever-expanding universe. The 20th century was a transformative period for our understanding of space, marked by groundbreaking discoveries that reshaped the landscape of cosmology. One of the most significant revelations came in the early 20th century, when Albert Einstein introduced his theory of general relativity. This theory fundamentally altered our perception of gravity, not merely as a force, but as the curvature of space-time itself. Einstein's work opened up new avenues for exploring the universe, allowing scientists to understand phenomena such as black holes and the expansion of the universe. Furthermore, the discovery of cosmic microwave background radiation in the mid-20th century provided critical evidence for the Big Bang theory. This faint afterglow of the universe's birth allows astronomers to glimpse the conditions of the early cosmos, unveiling the universe's history and supporting the notion that it has been expanding since approximately 13.8 billion years ago. This landmark finding not only validated theoretical predictions, but also ignited a new era of observational cosmology. The mid-century arrival of space exploration introduced an unprecedented perspective of our solar system and beyond. Launching satellites and sending humans into orbit allowed researchers to directly study celestial bodies, leading to discoveries such as the intricate features of Mars, the gas giants, and the potential for watery environments in places like Europa and Enceladus. The images and data gathered during these missions have been vital for understanding planetary geology, atmospheres, and the basic ingredients for life. Additionally, advancements in technology such as radio telescopes and deep space observatories propelled our ability to observe distant galaxies, nebulae, and other cosmic phenomena. The identification of quasars as extraordinarily bright objects powered by supermassive black holes hinted at the complexities of the universe. These discoveries, along with the realization that dark matter and dark energy comprise most of the cosmos, have challenged our perceptions and continue to invite deeper inquiries into the structure and fate of the universe. Each of these pivotal discoveries collectively illuminated a more intricate, dynamic cosmos, forever altering our quest for knowledge about the universe we inhabit. Science fiction has long served as a mirror reflecting society's hopes, fears, and aspirations regarding the universe and the possibilities of scientific exploration. From the early works of authors like H.G. Wells and Jules Verne through to contemporary films and television series, this genre has sparked curiosity about the cosmos and challenged our understanding of what exists beyond our planet. By imagining futures filled with space travel, alien civilizations, and advanced technologies, science fiction has the power to inspire scientists and lay people alike to contemplate the mysteries of the universe. For instance, the iconic series Star Trek introduced audiences to the concept of faster-than-light travel and the idea of a diverse galaxy filled with intelligent life forms. This imaginative narrative has not only entertained, but has also influenced real-life scientific inquiries and advancements. Engineers and scientists have drawn inspiration from the show to develop technologies we now take for granted, such as mobile phones and tablet computers. The portrayal of complex scientific theories in engaging, digestible formats has made abstract concepts more accessible to a broad audience, allowing for public discourse on topics like extraterrestrial life, artificial intelligence, and the implications of interstellar travel. Moreover, science fiction often tackles moral and philosophical questions surrounding scientific progress, pushing viewers to think about the potential consequences of their discoveries. Works like Arthur C. Clarke's 2001: A Space Odyssey explore the relationship between humanity and technology, provoking questions about evolution, consciousness, and our place in the universe. By posing these rich dilemmas, science fiction encourages critical thinking and ethical considerations that extend beyond the screen and into actual scientific communities and policymaking. As these narratives evolve alongside scientific discoveries, they continually shape the public's perception of what is plausible and possible in our exploration of the universe. From encouraging the next generation of scientists to dream big, to framing the discussions we have about our future, science fiction does more than entertain. It acts as a catalyst for inquiry and a bridge connecting imaginative ideas to the realities of scientific progress. The ancient site of Stonehenge has fascinated people for centuries, shrouded in mystery and intrigue. Located on the Salisbury Plain in England, this stone circle is not only an archaeological wonder, but also a remarkable example of astronomical alignment. Scholars propose that it was built around 5,000 years ago, yet its purpose remains largely speculative. Many theories suggest it served as a temple for celestial observance, a burial ground, or even a calendar to mark seasonal changes. The alignment of the stones with the movements of the sun and moon presents one of the most compelling aspects of Stonehenge's mystique. During the summer solstice, the rising sun casts its rays directly through the entrance, illuminating the central altar stone. This phenomenon suggests that the architects possessed advanced knowledge of solar cycles, indicating an understanding of astronomy that could rival some modern-day practices. Furthermore, the alignment with the setting sun during the winter solstice raises questions about the site's role in rituals related to death and rebirth. Additionally, the arrangement of the stone circle, as well as associated earthworks, reflects a conscious effort to connect the structure to the landscape. Researchers believe that the positioning may have been designed to align with specific stars, pointing towards a deeper cosmological significance infused in the beliefs of the people who built it. Evidence from nearby sites like Avebury adds layers to the mysteries, suggesting a broader network of sacred spaces that facilitated communal gatherings and astronomical observations. While much has been learned about its construction and potential uses, many questions remain unanswered. Did the builders leave any records, or had their intentions and knowledge been lost to time? As excavations continue and technology advances, each discovery invites further exploration of Stonehenge's relationship with the cosmos, hinting at our ancestors' desire to understand their place in the universe. The allure of Stonehenge persists, drawing researchers and visitors alike, all seeking connections between our past, the heavens, and what lies beyond. The invention of the spectrograph marked a significant turning point in the history of astronomical research, allowing scientists to delve deeper into the nature of celestial objects. Before this innovation, astronomers primarily relied on visual observations and what they could discern with the naked eye. However, once the spectrograph came into play in the late 19th century, the ability to analyze the light emitted, absorbed, or scattered by objects in space transformed our understanding of the universe. The spectrograph works by breaking down light into its component wavelengths, much like a prism spreads light into a rainbow. This analysis reveals a wealth of information about astronomical bodies. For instance, it can indicate the temperature, composition, density, and even motion of stars and galaxies. By studying the spectral lines produced when light interacts with matter, astronomers can identify specific elements and compounds, thereby determining what stars are made of light years away. Additionally, the spectrograph opened new avenues for the discovery of phenomena that were previously invisible. The Doppler effect, for example, enables astronomers to measure the velocity of stars and galaxies relative to Earth by observing shifts in the spectral lines. This capability led to groundbreaking findings, such as the discovery of the expanding universe and the evidence for dark energy, concepts that reshaped our understanding of cosmology. The impact of the spectrograph continues to resonate in modern astrophysics. The developments in spectroscopy have led to advancements in both observational techniques and theoretical frameworks, enhancing our grasp of everything from the life cycle of stars to the dynamics of distant galaxies. As technology progresses, spectroscopic techniques are expected to provide even more insights, ensuring that the cosmos continues to reveal its secrets through the language of light. The discovery of celestial objects has often been intertwined with significant historical milestones that have shaped human understanding of the universe. One prime example is the invention of the telescope during the early 17th century. This groundbreaking tool revolutionized astronomy and led to monumental discoveries. When Galileo Galilei pointed his telescope toward the night sky in the year 609, he revealed moons orbiting Jupiter and the phases of Venus, providing early evidence that not everything revolved around the Earth. This was a pivotal moment in the Copernican revolution, challenging the geocentric worldview that had persisted for centuries. Another key event unfolded in the year 1631, when Johannes Kepler formulated his laws of planetary motion after analyzing the observational data collected by Tycho Brahe. Kepler's work not only refined the understanding of planetary orbits, but also laid the groundwork for Isaac Newton's later formulation of universal gravitation in the late 17th century. These interlinked discoveries marked a shift towards a more precise and mathematical understanding of celestial mechanics, altering the course of scientific thought. The 19th century witnessed further notable strides with the discovery of the planet Uranus by William Herschel in the year 1781. This was the first planet discovered with a telescope and added a new chapter to the understanding of our solar system. Herschel's discovery prompted fascination and inquiry, leading the way for further exploration of the outer planets and eventually the field of astrophysics. The 20th century brought about a deepening exploration of the cosmos, highlighted by Edwin Hubble's discovery of galaxies beyond our Milky Way in the year 1924. His observations revealed that the universe is far more expansive than previously imagined, leading to the formulation of Hubble's law, which describes the expanding universe. This profound realization not only transformed our grasp of the cosmos, but also set the stage for revolutionary theories, including the Big Bang theory, which describes the origins of our universe. As scientific instruments have advanced, so too has our understanding of celestial objects, consistently reshaping both our scientific landscape and our place within the universe. Indigenous cultures across the world have had rich and diverse interpretations of celestial events, often intricately woven into the fabric of their daily lives, rituals, and storytelling. For many of these cultures, the night sky served not only as a navigational guide, but also as a canvas of spiritual significance. The movements of celestial bodies, such as the sun, moon, and stars, were seen as manifestations of ancestral spirits or deities, shaping agricultural practices, seasonal events, and ceremonial activities. Take, for instance, the Mayan civilization, which developed an exceptionally advanced understanding of astronomy. They meticulously tracked the cycles of the moon and planets, particularly Venus, which held particular importance in their calendrical systems. Their observations of celestial events allowed them to predict solar and lunar eclipses, which they viewed with both awe and trepidation. Such events often coincided with ritualistic practices, believed to appease the celestial forces that governed their world. Similarly, the Aboriginal peoples of Australia have maintained a deep connection with the stars, often using them to mark seasonal changes and guide their hunting and gathering. They have a rich oral tradition of stories that explain the positions of stars and constellations, often embedding valuable lessons and cultural knowledge within these narratives. For them, the sky is a living library where past events and future directions are written among the stars. In the northern regions, indigenous communities, including those in the Arctic, connected celestial events with their survival. The appearance of the aurora borealis, for example, was interpreted in various ways, often seen as a communication from ancestors. Understanding the cycles of celestial events was crucial for navigation, seasonal hunting, and cultural identity. These interpretations not only highlight a profound respect for the universe, but also showcase the fundamental ways in which humanity has sought meaning within the cosmos, blending science with cultural lore in an enduring dialogue with the skies above. Earth's geology plays a crucial role in how the planet interacts with cosmic events, particularly meteor strikes. When a meteor enters the atmosphere, it experiences immense heat and pressure, leading to its disintegration at high altitudes. However, larger meteors can reach the surface, and their impact creates craters, releasing energy equivalent to that of a nuclear explosion. The type of rock and sediment that makes up the bedrock will influence the size and shape of these craters. The geological features surrounding the impact site can also determine the aftermath of such events. For instance, strikes on rocky terrains may create sharp, distinct craters, while impacts on softer surfaces like clay or sand can lead to more dispersed and less defined depressions. These geological characteristics influence the way shock waves travel through the Earth, which can affect nearby ecosystems and even trigger seismic activity under certain conditions. Interestingly, Earth's geology has sometimes been shaped by these cosmic events. One famous example is the Chicxulub crater, caused by a meteor impact about 66 million years ago. This event is widely believed to have contributed to the extinction of the dinosaurs, illustrating how geological formations can not only bear witness to cosmic events, but also play a part in shaping the history of life on Earth. Moreover, the protective role of Earth's atmosphere cannot be understated. While it provides a shield against smaller meteors, larger impacts still pose significant threats to the terrain and life. Over time, the planet's geological processes, including erosion and tectonic activity, can obscure the evidence of these impacts, but they remain a testament to the dynamic interplay between Earth's geology and the cosmos. Solar flares, sudden bursts of radiation emitted by the sun, can have significant implications for Earth, particularly regarding technology and our atmosphere. These explosive events release energy equivalent to millions of hydrogen bombs, and while they may be awe-inspiring to observe, their effects can disrupt the delicate balance of our technological infrastructure. When a solar flare occurs, it produces energetic particles that can reach Earth within minutes. These charged particles interact with the Earth's magnetosphere, leading to geomagnetic storms. Such storms can interfere with satellite operations, including navigation systems, telecommunications, and satellite imaging. Astronauts aboard the International Space Station might also be at risk due to increased radiation levels during these events, necessitating protective measures while they orbit above us. Moreover, solar flares can induce currents in power lines, leading to potential voltage spikes that may compromise electrical grids. Instances of power outages have been documented when geomagnetic storms caused by solar activity engaged with the Earth's surface systems. Thus, monitoring solar activity has become crucial for energy stability, especially in regions with high latitude, where the effects of such storms are more pronounced. The atmosphere itself is affected too. Solar flares can increase the density of the upper atmosphere by heating it. This effect can influence the orbits of satellites and even space debris, adding another layer of complexity to space operations. Understanding and predicting solar flares' impact is essential as our reliance on technology grows, making continuous research and monitoring necessary to safeguard our digital world against these cosmic phenomena. Cosmic events like supernovae, which are the explosive deaths of massive stars, wield tremendous influence over the cosmos. When a star reaches the end of its life after exhausting its nuclear fuel, it ejects its outer layers into space at incredible speeds. This explosion not only releases an extraordinary amount of energy, but also scatters elements forged in the star's core throughout the universe. These elements, such as carbon, oxygen, and iron, are the building blocks of life as we know it. One could argue that without the remnants of ancient supernova, the rich chemistry required for life on Earth may never have formed. When a supernova occurs close enough to our planet, there can be more direct consequences. These cosmic explosions emit intense bursts of radiation, including gamma rays, which could have damaging effects on the atmosphere. If a supernova were to happen within around 100 light-years from Earth, it might disrupt the ozone layer, which protects our planet from harmful ultraviolet radiation. This could potentially impact life on Earth in various ways, from increased mutation rates among organisms to disruptions in climate patterns. Interestingly, evidence suggests that supernovae may have played a role in mass extinction events throughout Earth's history. For example, some scientists believe that a series of supernovae, active around the time of the Ordovician-Silurian extinction, contributed to changing environmental conditions that may have led to dramatic shifts in biodiversity. Such cosmic events remind us that the universe is not a silent backdrop, but a vibrant participant in our planet's history, influencing the development and extinction of life through both its fiery explosions and the elements they forge. The sheer scale of these cosmic phenomena emphasizes the interconnectedness of all things in the universe. While supernovae might seem distant and abstract, their repercussions resonate down to our planet, shaping the very elements of existence and the evolutionary path life has taken over millions of years. Earth's magnetic field plays a crucial role in protecting life on our planet from harmful cosmic radiation. Generated by the movement of molten iron within its outer core, this magnetic field extends far into space, forming a protective cocoon known as the magnetosphere. This invisible shield stands between us and the relentless bombardment of charged particles emitted by the Sun and other cosmic sources. These particles, primarily protons and electrons, travel at incredible speeds and can be detrimental to living organisms. Without the magnetic field, these cosmic rays would collide with the Earth's atmosphere and surface, potentially causing damage to our DNA and increasing the risk of cancer and other health issues. However, the magnetosphere deflects most of these charged particles, guiding them away from the Earth's surface and preserving our atmosphere and biological integrity. An interesting aspect of this magnetic shield is its dynamic nature. The magnetosphere is not uniform. It fluctuates in response to solar activity. During events such as solar flares or coronal mass ejections, the magnetic field's protective qualities strengthen or change shape, adapting to the incoming threat. This adaptability is vital, as it ensures that we continue to receive the benefits of cosmic radiation's minimal levels while avoiding the harmful peaks associated with solar storms. Understanding Earth's magnetic field not only reveals its significance for our health, but also highlights our planet's unique position in the cosmos. It fosters an environment conducive to life by shielding us from the dangers of space, demonstrating the intricate balance of natural forces that support our existence. The connection between climatological events on Earth and astronomical phenomena is a fascinating aspect of how our planet operates within the vast universe. At the heart of this relationship lies the concept of energy, particularly from the Sun. The Sun's radiation plays a crucial role in determining Earth's climate, and it is also influenced by celestial events such as solar flares and sunspots. Solar flares, which are bursts of energy from the Sun, can affect the Earth's atmosphere by altering temperature and weather patterns, as well as impacting communication systems. Beyond the Sun, the effects of astronomical bodies like the Moon have been observed in correlation with Earth's climate. The gravitational pull of the Moon is a primary force behind ocean tides, but its influence extends to atmospheric patterns as well. Research has indicated that the alignment of the Moon and the Sun can contribute to the occurrence of extreme weather events such as storms and heavy rainfall. The cyclical nature of the Moon's phases can lead to variations in atmospheric pressure, which can also influence climate. Furthermore, long-term astronomical phenomena, such as the Milankovitch cycles, shift the Earth's orbit and axial tilt over tens of thousands to hundreds of thousands of years. These changes affect the distribution of solar energy received by the Earth, leading to profound shifts in climate, including glacial and interglacial periods. Scientists analyze sediment cores and ice cores to understand past climate conditions and how they correlate with these astronomical cycles. Additionally, cosmic events, such as supernovae or variations in cosmic ray intensity, could affect the Earth's climate over extensive timescales. Cosmic rays influence cloud formation, and fluctuations in their intensity might alter weather patterns. While the direct link between these events and immediate climatological changes is still under investigation, It provides a compelling illustration of how interconnected our world is with the cosmos, revealing a delicate dance between atmospheric conditions and celestial phenomena. Ancient geoglyphs, those large-scale designs formed on the Earth's surface, reveal fascinating connections to astronomical events and alignments. Cultures from various parts of the world created these monumental artworks, often with intentions that reflected their understanding of the cosmos. For many ancient societies, the movements of celestial bodies were not merely a backdrop for daily life, but crucial elements that informed their calendars, agricultural practices, and spiritual beliefs. In the case of the enigmatic Nazca lines in Peru, for example, researchers have noted that several figures align with specific solar and lunar events. Certain geoglyphs point towards the sunrise on the summer solstice or the sunset on the winter solstice, suggesting a purposeful design to track these astronomical changes. This connection demonstrates that the creators were not only artists, but also keen observers of the sky, incorporating their findings into their cultural expressions. These ancient civilizations often embedded their understanding of celestial phenomena in their landscapes. The geoglyphs served as markers or reminders of events that held significance in their spiritual and agricultural cycles. For instance, aligning a geoglyph with a celestial event could signify a time for planting or harvesting, further integrating their awareness of the cosmos into their everyday lives. The importance of these alignments stretches beyond simple observation. They signify a sophisticated understanding of astronomy that is both practical and symbolic. Through these monumental structures, ancient peoples conveyed their reverence for the universe, forging an enduring bond between the earth and the heavens. This relationship continues to intrigue archaeologists and astronomers alike, highlighting a rich tapestry of human knowledge and experience in regard to the cosmos. The Moon plays a crucial role in stabilizing Earth's climate and environment, primarily through its gravitational influence. This relationship helps to moderate the tilt of Earth's axis. As our planet rotates, it is tilted at an angle of approximately 23 degrees. This tilt is critical as it affects the distribution of sunlight across the globe, leading to seasonal variations. Without the Moon's stabilizing presence, Earth could experience significant fluctuations in axial tilt, resulting in extreme changes in climate over time. Additionally, the Moon contributes to the creation of our tides. As it orbits Earth, its gravitational pull creates bulges of water in the oceans, leading to high and low tides. These tidal movements are not just a fascinating phenomenon, they play a vital role in shaping coastal ecosystems and influencing marine life. The ebb and flow of the tides help distribute nutrients and support various habitats, which are essential for biodiversity. The impact of the Moon extends beyond the oceans. Its gravitational influence also affects atmospheric circulation patterns, which can help maintain a more stable climate. By working in tandem with solar energy and Earth's rotation, the Moon's presence helps create a delicate balance that nurtures the conditions necessary for life to thrive. Moreover, the absence of the Moon would likely have resulted in a much different Earth, one that might not have sustained the same complex ecosystems and weather patterns we observe today. Thus, the Moon, though it may appear as a silent guardian in the night sky, plays an active and dynamic role in securing a stable, flourishing environment on our planet. Astrobiology, the study of life in the universe, provides us with a fascinating lens through which we can examine Earth's own evolution. By exploring the potential for life on other planets, scientists gain insights into the conditions that support life and how these conditions have shaped our planet over billions of years. For instance, the search for extremophiles, organisms that thrive in extreme environments, reveals the remarkable adaptability of life, suggesting that life on Earth may have begun in some of the harshest conditions found in deep-sea hydrothermal vents or frozen tundras. Furthermore, astrobiology helps us understand planetary processes that influence habitability. The study of other celestial bodies, such as Mars or the icy moons of Jupiter and Saturn, allows researchers to compare geological and atmospheric conditions across different worlds. Discovering organic molecules or signs of ancient water on these planets not only informs us about the potential for past life beyond Earth, but also raises questions about similar ancient processes on our own planet. Understanding how Earth's climate and geology have transformed can lead to revelations about how life adapted or even emerged during critical environmental shifts. Another compelling aspect of astrobiology is the examination of how life interacts with and alters its environment. By tracing the history of Earth's biosphere, scientists can identify significant events such as the Great Oxygenation Event, where cyanobacteria produced oxygen, dramatically changing the atmosphere and paving the way for more complex life. Comparing this with potential biosignatures on exoplanets allows scientists to hypothesize about when and how life might develop, not just on Earth, but across the galaxy. This field also illuminates the role of biology in planetary systems. For instance, understanding the biochemical processes that enable life not only aids in identifying habitable conditions, but also reveals the interconnectedness of life and the physical world. By studying the fundamental principles of life, astrobiologists draw connections between the origins of life, its evolution, and the conditions necessary for sustaining that life, creating a deeper understanding of our place in the cosmos and the intricate dance of factors that foster our existence here on Earth. Ice cores, which are cylindrical samples extracted from ice sheets and glaciers, provide a remarkable archive of Earth's climate history. Within these layers of ice, scientists have discovered entrapped gases, dust, and even isotopes that tell stories of past atmospheric conditions. One particularly fascinating aspect is the presence of certain elements and compounds that are indicative of cosmic impacts, such as those resulting from asteroids or comets colliding with our planet. Research has highlighted spikes in specific isotopes, like those of beryllium or iridium, found in layers corresponding to known impact events. These isotopes are created when high-energy cosmic rays interact with the Earth's atmosphere. For instance, after a significant cosmic impact, the ensuing dust and debris can lead to an increase in the concentration of these isotopes in the ice layers. Such findings correlate with known geological records of extinction events and mass extinctions, making it a compelling connection to Earth's tumultuous past. Additional evidence includes microscopic particles such as soot and glass, formed from the intense heat during an impact event. These materials can be preserved within the ice and serve as a physical reminder of a catastrophic event that changed life on Earth dramatically. For instance, the impact associated with the extinction of the dinosaurs, often linked to the Chicxulub impactor, left traces that can be traced through such ice core analyses. The study of ice cores thus not only reveals the history of climate variations, but also acts as a time capsule showcasing the profound effects cosmic events have had on our planet. By piecing together these layers of ice, scientists can unravel the complex interplay between cosmic impacts and Earth's geological and biological history, enriching our understanding of both the planet's past and the universe's reach into our world. Seasonal changes, long understood through the tilt of the Earth's axis and its orbit around the Sun, are also intricately linked to solar activity. This activity consists of changes in the solar output due to phenomena like sunspots, solar flares, and coronal mass ejections. These shifts in solar energy can significantly influence the Earth's atmosphere, leading to changes in climate and seasonal patterns. During periods of high solar activity, an increase in solar radiation can lead to warmer temperatures in certain regions, particularly those that are already in the Sun's direct path. Conversely, lower solar activity can correlate with cooler temperatures and potentially harsher winters. This connection becomes even more complex when considering the role of solar cycles, which typically span about 11 years. Scientists have observed that these cycles can create noticeable shifts in weather patterns, although the precise mechanisms remain a subject of investigation. One of the fascinating mysteries surrounding this relationship lies in understanding how solar activity not only affects temperatures, but also impacts weather extremes. Some researchers speculate that the Sun's magnetic field could influence the jet stream, which dramatically shapes weather phenomena across the globe. This interdependence raises questions about how much of Earth's climate is inherently tied to solar activity versus other factors such as greenhouse gases or ocean currents. Unraveling these mysteries is crucial, especially when considering the implications of our changing climate. As humans alter the atmosphere, scientists seek to determine how these alterations may interact with natural solar cycles. This research is not just about understanding seasonal changes, it is also pivotal for future predictions of climate patterns and potential disasters. Such insights could enhance preparedness for extreme weather events that are increasingly frequent in our modern world. Looking ahead to the exciting future of space exploration, several ambitious missions are set to deepen our understanding of distant planets within our solar system and beyond. One of the most anticipated missions is the Mars Sample Return, which aims to bring back soil and rock samples from Mars to Earth. This collaborative effort between NASA and the European Space Agency is designed to uncover clues about the planet's past, particularly its potential to harbor life. Another significant venture is the Europa Clipper mission, which is scheduled to launch in the coming years. This mission will focus on Jupiter's moon Europa, a body believed to have a subsurface ocean beneath its icy crust. Scientists are particularly interested in investigating the moon's potential habitability, as the ocean may harbor the necessary ingredients for life. With an array of sophisticated instruments, Europa Clipper aims to gather detailed data about the moon's atmosphere, surface composition, and geology. Not to be overlooked is the Dragonfly mission to Titan, Saturn's largest moon. Slated for launch in the year 2027, Dragonfly will employ a unique rotorcraft to traverse the alien landscape. Titan boasts lakes of methane and ethane, and the mission seeks to explore its intriguing chemistry, potentially shedding light on prebiotic processes that may resemble those on early Earth. Furthermore, the James Webb Space Telescope is poised to revolutionize our understanding of distant exoplanets. While not a planetary mission in the traditional sense, it is designed to analyze the atmospheres of planets orbiting other stars. By collecting light from these distant worlds, the telescope aims to identify chemical signatures that could indicate the presence of life-sustaining elements. The insights gleaned from this mission could transform our perspective on life beyond our planet. With all these groundbreaking endeavors on the horizon, the next decade promises to be a thrilling chapter in the story of space exploration. The Artemis program is a bold initiative led by NASA with the ambitious goal of establishing a sustainable human presence on the Moon by the end of this decade. Central to this mission is the development of advanced technologies and infrastructure that will support long-duration stays on the lunar surface. By focusing on sustainability, Artemis seeks not just to visit the Moon, but to create a permanent base that can facilitate scientific research and exploration. One of the key components of Artemis is the Lunar Gateway, a space station that will orbit the Moon, serving as a hub for astronauts traveling to and from the lunar surface. This gateway will provide a platform for various missions and operations, greatly enhancing access to the Moon. It will enable astronauts to stage missions, conduct experiments, and even perform repairs using resources gathered from the Moon itself, significantly reducing the need for supplies transported from Earth. Moreover, the program emphasizes utilizing lunar resources, a concept known as in situ resource utilization. By harnessing water ice potentially found in the shadowed craters of the Moon, astronauts could produce oxygen and hydrogen, which are not only vital for breathing, but can also serve as rocket fuel. This opens up new possibilities for sustained exploration, allowing for longer missions and furthering human understanding of the Moon and beyond. Artemis does not stop at just returning humans to the lunar surface. It aims to build a foundation for future exploration, including eventual missions to Mars. The experience and knowledge gained from establishing a sustainable presence on the Moon will be invaluable in planning for human journeys to other celestial bodies, marking a significant step in humanity's quest to explore the universe. Among the exciting frontiers of research and development for deep space exploration lies an array of advanced technologies that could significantly transform our understanding of the cosmos. One of the most promising initiatives is the development of next-generation propulsion systems. Traditional rocket propulsion methods will reach their limits as missions aim for more distant targets. Innovative solutions like ion propulsion, which utilizes electric fields to accelerate ions for thrust, offer the potential for far more efficient travel, drastically reducing the time required to reach distant planets and beyond. Robotic spacecraft are also evolving at an astonishing rate, designed to perform not only exploratory tasks, but also complex analyses on remote worlds. The newly designed autonomous drones are equipped with artificial intelligence capabilities, enabling them to make real-time decisions and navigate treacherous landscapes without direct human control. This autonomy is crucial when operating light years away, where the delay in signal transmission makes immediate communication impossible. Additionally, advancements in communication technology are essential for deep space exploration. Increasing data transmission rates through laser communication systems, which use light instead of radio waves, could dramatically enhance the ability to send and receive vast amounts of information across the expanses of space. This leap in technology would enable scientists to receive high-resolution images and an abundance of scientific data from far-flung missions almost instantly. Power generation and storage are also critical areas of development. As missions venture farther from the Sun, conventional solar panels may lose effectiveness. Innovative solutions, such as compact nuclear reactors and radioisotope thermoelectric generators, provide reliable, long-lasting energy sources capable of supporting spacecraft and their instruments for years or even decades. With these technologies, humanity's reach within the universe continues to broaden, unveiling the mysteries of our solar system and beyond. Missions to Mars hold the potential to revolutionize our understanding of life and the conditions necessary for habitability. Mars, often referred to as Earth's twin, presents a unique opportunity to explore the history of water and geology, elements crucial in determining whether the planet ever supported life. Evidence suggests that ancient rivers, lakes, and possibly even oceans existed on its surface billions of years ago. By investigating sedimentary deposits and geological formations, scientists can piece together a narrative about past environmental conditions, which could reveal whether life ever thrived there. The search for microbial life is at the forefront of these missions. Robotic landers and rovers are equipped with advanced scientific instruments designed to analyze soil and rock samples for organic compounds and biosignatures. If these missions uncover traces of past life, it would not only confirm that life can exist beyond Earth, but also challenge our comprehension of how life originates and survives in diverse environments. Such findings could lead to new hypotheses about the conditions required for life, reshaping our perspective on the possibility of life elsewhere in the universe. Missions to Mars also emphasize the importance of astrobiology, a field dedicated to studying the potential for life in extreme environments. By examining the Martian climate and its capacity to support life, scientists can refine their criteria for habitability, which could change our search parameters when looking at exoplanets orbiting distant stars. If Mars, with its harsh conditions, previously sustained life forms, it would suggest that other seemingly inhospitable worlds might also harbor life beneath their surfaces. As these missions advance, they will not only enhance our knowledge of Mars, but also inspire future explorations of other celestial bodies. The methodologies developed during these endeavors could be applied to icy moons and distant planets, deepening our quest to understand if life is a universal phenomenon. Each discovery on Mars could echo across the cosmos, informing our ongoing search for life and habitability beyond our home planet. Planning a crewed mission to the outer planets presents an array of formidable challenges that stretch the limits of current space exploration capabilities. One of the primary concerns is the extended duration of such a journey. Traveling to planets like Jupiter or Saturn requires spacecraft to traverse vast distances, often lasting several years. This means that astronauts must endure prolonged periods in a confined environment, which raises significant questions about mental health, social dynamics, and physical well-being. The harsh conditions of space further complicate the mission. As the spacecraft ventures away from the Sun, it encounters extreme temperatures and increased radiation levels from cosmic sources. Protecting astronauts from this radiation is essential, as it can lead to long-term health issues such as cancer or damage to the central nervous system. Developing effective shielding techniques is a crucial aspect of ensuring the safety and longevity of the mission crew. Another critical challenge involves the need for reliable life support systems. Given the distance from Earth, resupply missions would be impractical, making it vital to create autonomous systems capable of recycling air and water, growing food, and processing waste. Research into closed-loop life support systems is ongoing, but scientists must ensure these systems can function effectively for several years without human intervention. Lastly, the technology required for propulsion, communication, and navigation poses significant hurdles. Current propulsion systems may not be sufficient for the speed and efficiency needed for such long journeys. Innovative solutions like nuclear propulsion or solar sails are being explored, yet they remain in developmental stages. Additionally, maintaining communication with Earth becomes increasingly difficult as distance grows, necessitating the development of reliable systems that can overcome the delays in signal transmission. Each of these challenges must be addressed cohesively, paving the way for successful human exploration of our solar system's outer reaches. Private space companies have become pivotal players in cosmic exploration, significantly enhancing the scope and pace of our ventures into the universe. With their innovative approaches, they are not only reducing costs, but also increasing access to space for diverse scientific missions. Companies like SpaceX, Blue Origin, and Virgin Galactic have revolutionized space travel by developing reusable rocket technologies. This advancement allows for a dramatic decrease in the expense of launching payloads into orbit, thereby making space more accessible for scientific research and exploration. One remarkable aspect of private contributions to cosmic exploration is their ability to foster collaboration with governmental space agencies. Agencies like NASA have been able to leverage the capabilities of private firms for missions that would have been prohibitively expensive or logistically challenging on their own. For instance, through contracts for resupply missions to the International Space Station, private companies provide essential support to ongoing research while simultaneously developing their own technologies for future endeavors. This synergy advances scientific knowledge and builds a more robust presence in space. Moreover, private firms are venturing beyond low Earth orbit, setting their sights on the Moon and Mars. For instance, SpaceX's ambitious plans for interplanetary travel envision not just sending astronauts to Mars, but also establishing a sustainable human presence there. Such enterprises inspire a new generation of scientists and engineers to pursue careers in space exploration. With the promise of groundbreaking missions and potential colonization, enthusiasm for space initiatives has surged, inviting contributions from a wide array of talent. The rise of private space companies has also sparked a wave of innovation in developing small satellite technologies. These smaller, cost-effective satellites play crucial roles in environmental monitoring, climate change research, and telecommunications. As these companies experiment with new methods of satellite deployment, they expand our capabilities for observing and understanding both our planet and the vast universe beyond it. The participation of private industry brings a fresh dynamism to cosmic exploration, revealing possibilities that were once confined to our imagination. Jupiter and Saturn, the giants of our solar system, are surrounded by numerous moons, many of which hold tantalizing secrets beneath their icy exteriors. One of the most intriguing is Europa, one of Jupiter's largest moons. Researchers believe that beneath its thick layer of ice lies a global ocean of liquid water. The potential for life in such an environment makes Europa a prime candidate for exploration. Scientists are particularly curious about the possibility of life forms that could thrive in these harsh conditions, perhaps analogous to the extremophiles found in Earth's deep oceans. Further intrigue comes from Ganymede, another of Jupiter's moons, which also appears to have a subsurface ocean. Ganymede is unique in that it is the only moon known to have its own magnetic field, which raises interesting questions about its internal structure and the interactions between its ocean and the surrounding environment. This magnetic field may provide clues about the moon's geological history and its potential to host life. Saturn's moons, especially Enceladus and Titan, present their unique mysteries. Enceladus has geysers that erupt jets of water vapor and ice particles into space. This discovery hints at a complex and active interior, suggesting the presence of an ocean beneath its icy surface as well. The organic molecules found in these plumes add another layer of excitement around the possibility of life. Meanwhile, Titan, Saturn's largest moon, stands out for its dense atmosphere and lakes of methane and ethane. The chemistry occurring on Titan is vastly different from that on Earth, yet it opens the door to exploring alternative forms of life that might exist. These moons offer a glimpse into environments that diverge from our terrestrial experience. The exploration of these celestial bodies could revolutionize our understanding of the potential for life in the cosmos and the processes that govern the evolution of water worlds. As missions to these moons are planned, the scientific community eagerly anticipates what secrets these distant satellites may reveal, changing our perspective on life in the universe. Future telescopes promise to transform our understanding of distant galaxies by incorporating advanced technologies that enhance their observational power. These innovations will allow astronomers to peer deeper into the cosmos than ever before, gathering light from objects that are billions of light-years away. By utilizing larger mirrors and improved detectors, these instruments can capture fainter light, revealing details that current telescopes struggle to discern. Technologies like adaptive optics will improve image clarity, compensating for atmospheric distortion that blurs ground-based observations. This means that telescopes could provide sharper images and more precise data, allowing scientists to analyze the structures and compositions of distant galaxies. Furthermore, advancements in infrared and radio wavelengths will enable the exploration of celestial phenomena that are invisible to traditional visible light telescopes. This includes the study of cooler objects and nebulas, which contribute to star and galaxy formation. Moreover, with the capability to survey the entire sky and conduct extensive surveys of galaxy populations, future telescopes can gather a wealth of data in a shorter time. This efficiently allows researchers to map the distribution of galaxies across the universe, shedding light on their evolution and the processes that govern their formation and interaction. Enhanced digital processing and machine learning algorithms also promise to assist in analyzing the enormous amounts of data generated, helping to identify patterns and make connections that inform our understanding of cosmic history. As we look to the future, telescopes like the James Webb Space Telescope and its successors are set to usher in a new era of discovery. They hold the potential to answer fundamental questions about the origins of galaxies, the presence of life beyond our own, and the structure of the universe as a whole, revealing a cosmos filled with untold wonders waiting to be uncovered. International collaborations serve as the backbone of advancing cosmic research, fostering a spirit of unity among scientists around the world. These partnerships enable research teams from different countries to pool their expertise, resources, and technologies to tackle complex questions about the universe. The vastness and complexity of cosmic phenomena require a diverse range of perspectives and skill sets that can only be achieved through collaborative efforts. One compelling example of such collaboration is the International Space Station, where scientists from numerous nations conduct experiments that orbit Earth. These initiatives not only facilitate a better understanding of microgravity's effects, but also lay the groundwork for future deep space exploration. Across borders, astrophysicists work together on projects like the Event Horizon Telescope, which produced the first image of a black hole in 2019. This achievement was made possible through the collective effort of hundreds of scientists analyzing data from a global network of radio telescopes. Research stations and observatories established in various countries further exemplify the power of collaboration. The European Southern Observatory, located in Chile, is a prime example, providing astronomers from multiple nations access to some of the best dark sky conditions on Earth. Sharing equipment, funding, and findings leads to breakthroughs that none could accomplish alone. Also, international partnerships help to mitigate the costs of ambitious endeavors, such as the development of next-generation telescopes and missions to distant planets. Moreover, these collaborations foster the exchange of knowledge and cultural understanding, creating a global community of scientists dedicated to unraveling the universe's mysteries. As discoveries are made and new questions arise, the importance of working together only grows. By uniting their efforts, researchers can ensure that cosmic research continues to thrive in an increasingly interconnected world. Advancements in propulsion technology are transforming our understanding of what is possible in space travel. Traditional rocket engines, primarily reliant on chemical propellants, have served humanity well, but come with significant limitations. These engines work on the principle of Newton's third law, where thrust is generated by expelling mass in one direction, allowing a spacecraft to move in the opposite direction. While effective for launching payloads to low Earth orbit, the efficiency of these fuels dwindles for deeper space missions, leading to long travel times. Emerging technologies like ion propulsion and solar sails are beginning to shift this paradigm. Ion propulsion systems generate thrust by accelerating ions using electric fields, resulting in a highly efficient use of fuel. This method allows spacecraft to continue accelerating over time, enabling travel to distant celestial bodies in a fraction of the time compared to conventional methods. For instance, missions such as the Dawn spacecraft have successfully demonstrated these capabilities, exploring asteroids and providing valuable data about the early solar system. Additionally, the concept of solar sails harnesses the pressure of sunlight itself to propel ships through space. By using large reflective surfaces that catch photons from the sun, these sails can gradually accelerate a spacecraft without the need for fuel. With advancements in materials science, the potential for robust solar sails is becoming increasingly viable, allowing for deep space exploration with minimal resource expenditure. This could open doors to missions previously deemed too distant or impractical. As researchers continue to develop and refine these and other innovative propulsion methods, the implications are profound. Not only could we reach distant planets and potentially habitable moons within our solar system, but the prospects for missions to other star systems become more tangible. The dream of interstellar travel, once confined to science fiction, is inching closer to reality with every step forward in propulsion technology, igniting imaginations and expanding our horizons in the universe. The study of the universe profoundly influences our understanding of time and existence, reshaping our perceptions of what these concepts truly mean. Scientists have discovered that time is not a fixed entity, rather, it is intricately linked to the very fabric of the cosmos. Through the theory of general relativity developed by Albert Einstein, we learn that time can bend and stretch depending on gravitational forces. For instance, time flows differently in stronger gravitational fields compared to weaker ones, leading to the phenomenon known as time dilation. This means if you were to spend time near a black hole, you would age more slowly than someone far away. Furthermore, our exploration of the universe has revealed that time itself may have a beginning and potentially an end. The Big Bang theory posits that about 13.8 billion years ago, the universe began from an incredibly dense and hot state, marking not just the birth of space but also the beginning of time as we know it. As we study cosmic microwave background radiation, which serves as a remnant of the early universe, we gain insights into the conditions of that primordial moment, allowing us to think about our existence in a temporal framework. As we observe the universe expanding, questions arise about the future and the ultimate fate of time itself. Some cosmologists speculate on concepts such as the heat death of the universe, where everything would eventually reach a state of uniformity and entropy, leading to a universe devoid of usable energy and, consequently, events over time. This illustrates how our understanding of existence is dynamically linked to the cosmos's vast and ever-evolving nature. Moreover, the cosmic perspective invites us to ponder our place within this magnificent universe. The mere act of recognizing that we are composed of star stuff, created in the hearts of stars that have exploded into supernovae, connects existence to the larger tapestry of the cosmos. In understanding the universe, we not only learn about the laws that govern it, but also come to appreciate our transient existence in the grand timeline of a cosmic story that is both ancient and continually unfolding. The potential discovery of extraterrestrial life brings with it a myriad of ethical considerations that challenge our understanding of existence, identity, and responsibility. Among the primary concerns is the question of rights. If we were to establish contact with extraterrestrial beings, what rights would they possess? This inquiry urges us to reassess the ethical frameworks we apply to living entities, expanding our perspective beyond Earth-centric viewpoints to consider the potential complexities of alien life forms. Scientific exploration is also at the heart of these ethical discussions. The quest for knowledge is a powerful motivator for humanity, but with it comes the responsibility to handle any newfound intelligence with caution and respect. There is a genuine fear that our actions might lead to exploitation or harm. Just as we debate the ethics of animal rights on our own planet, so too must we tread carefully in how we interact with any discovered life beyond Earth, ensuring we do not repeat past mistakes of colonization and ecological disregard. Additionally, the implications for our societal norms and cultural frameworks cannot be overstated. A revelation of extraterrestrial life would prompt significant philosophical debates about our place in the universe. It could challenge long-held beliefs about individuality, spirituality, and human exceptionalism. Consequently, the impact on psychological and sociological dynamics within humanity would be profound as we reconcile our identity in light of coexistence with other sentient beings. To navigate these complex questions, open dialogue among scientists, ethicists, and the broader public is essential. Establishing guidelines and frameworks informed by diverse perspectives could help ensure that any engagement with extraterrestrial life is characterized by respect, caution, and a commitment to uphold the values of dignity and coexistence. This process can prepare society for whatever truths the cosmos might reveal, promoting a responsible approach to one of humanity's most profound challenges. Advanced space exploration could dramatically reshape humanity's destiny and its underlying philosophies. As we venture further into the cosmos, we are likely to confront profound questions about our place in the universe. This exploration could lead to discoveries that redefine our understanding of life, existence, and our unique position in the vastness of space. For instance, finding microbial life on other planets would challenge the long-held belief that Earth is the only cradle of life, potentially altering our views on life's origin and nature. Moreover, the technologies developed for interstellar travel and habitation might create advancements that benefit life on Earth. Innovations in energy efficiency, sustainable living, and material science could emerge from the challenges posed by space travel. This connection between what we learn in space and its applications on our home planet could foster a renewed sense of stewardship toward Earth and its resources, prompting us to consider our responsibility to both our planet and any celestial bodies we explore. As humanity unites in pursuit of common goals beyond our home, exploration could enhance global collaboration and change our philosophical stance on borders and divisions. Facing the challenges of space missions might encourage us to see ourselves as part of a single human family, fostering a collective identity that surpasses national and cultural boundaries. The consequent shifts in perspective could inspire a greater emphasis on peace and cooperative endeavors. Finally, the possibility of colonizing other planets invokes ethical debates about exploration and exploitation. As we look outward for new homes, considerations about ownership, environmental sustainability, and the rights of potential extraterrestrial life form the crux of a new philosophical dialogue. These discussions could lead to novel frameworks for how society functions, shaping not only our destiny, but also the moral compass guiding humanity's advancements in this new frontier. The journey into space, thus, is not merely a leap into the unknown, but a transformative voyage that holds the potential to redefine who we are as human beings. Contemplating the vastness of the universe can evoke a range of psychological effects, deeply impacting our sense of self and our place within the cosmos. For many, this expansive thought prompts feelings of awe and wonder. Faced with galaxies that contain billions of stars and planets, individuals often experience a humbling recognition of their own insignificance in the grand scheme of things. This realization can lead to a profound shift in perspective, encouraging a desire to understand not only the universe, but also the intricate connections that bind all life. However, alongside feelings of awe, the enormity of the universe can also stir feelings of existential anxiety. The mere thought of an infinite universe can lead to questions about purpose, meaning, and the role humanity plays in a seemingly indifferent cosmos. This confrontation with such vastness may intensify the search for personal significance, prompting both philosophical reflection and at times a sense of helplessness. It can lead some to seek comfort in spirituality or community as they grapple with these existential questions. Conversely, the contemplation of the universe can also foster curiosity and a drive for exploration. The mysteries of dark matter, black holes, and cosmic evolution ignite imaginations and inspire scientific pursuits. People often find motivation in studying the stars, allowing this curiosity to transform feelings of anxiety into excitement. Such engagement with the cosmos can promote mental well-being, encouraging individuals to feel connected to something larger than themselves. Moreover, this cosmic perspective often strengthens appreciation for life on Earth. When individuals grasp the fragility of our planet amid vast celestial expanses, they may foster a deeper connection and responsibility toward the environment and each other. This can cultivate a sense of unity, reminding us that despite our differences, we share a common home in an astonishingly expansive universe. The profound discoveries across the cosmos often bring a refreshing perspective to religious and spiritual beliefs, challenging them while simultaneously offering opportunities for reinforcement. As humanity has gazed deeper into the universe, we have unveiled revelations about the bounds of existence, the origins of the universe, and the nature of reality itself. For many, these scientific insights can provoke questions about the purpose and design of life, compelling a re-evaluation of spiritual tenets that have long guided belief systems. For instance, the understanding that the universe began with a singular event known as the Big Bang can stir debate among those who subscribe to creation narratives found in various religious texts. While some may feel that science contradicts their beliefs, others find that this cosmic history aligns with or enriches their understanding of creation. The notion that humanity exists in a vast, ever-expanding universe can be a humbling experience, prompting reflections on our place in existence and invigorating discussions about a creator or higher power. Moreover, the search for extraterrestrial life raises intriguing spiritual questions. Discovering that we are not alone in the universe may lead to new contemplations about the divine and how it manifests across different forms of existence. Such discoveries amplify the idea that life, in its myriad forms, might be part of a larger cosmic tapestry woven with intention or chance. In this light, both science and spiritual inquiry could converge, suggesting that both play vital roles in enriching our understanding of existence. Conversely, scientific advancements can be unsettling for certain religious frameworks, prompting a crisis of faith for some individuals. As the mysteries of the universe are unraveled, from quantum mechanics to the extensive scale of cosmic evolution, the implications may challenge traditional interpretations of sacred texts. Nevertheless, believers often reconceptualize their faith in light of new findings, leading to a dynamic dialogue between science and spirituality that continues to evolve with each cosmic breakthrough. Significant discoveries in astrophysics have the potential to reshape society in profound ways. As we unlock the secrets of the universe, our understanding of existence itself could shift, influencing philosophical and spiritual beliefs about our place in the cosmos. When we learn more about fundamental questions regarding the nature of dark matter, black holes, or the possibility of extraterrestrial life, it can inspire a re-evaluation of our human identity and relationships with one another. Technological advancements that stem from astrophysical research can lead to innovations that have widespread practical applications. For example, developments in imaging techniques or data processing, initially designed for studying distant stars and galaxies, often find their way into medical technologies, environmental monitoring, and telecommunications. This cross-pollination of ideas fosters an atmosphere of curiosity and encourages the next generation to pursue careers in science and engineering, which can ultimately drive the economy and enhance societal progress. Moreover, the The quest to explore outer space encourages global collaboration. International space missions and cooperative research initiatives highlight the need for countries to work together toward common goals. This unity can transcend barriers, promote peace, and cultivate a shared sense of humanity as we all look toward the stars. Such collaborations can further fuel discussions about addressing global challenges, like climate change or humanitarian issues, as the same spirit that drives space exploration can be applied to problems on Earth. As we make strides in understanding our universe, we may also experience a heightened sense of responsibility toward our planet. Discoveries that illustrate the fragility of celestial bodies or the interconnectedness of ecosystems prompt society to rethink its priorities. The realization that Earth is but a small oasis in a vast universe can evoke a more profound respect for our home and incentivize actions that promote sustainability and conservation. With each revelation from the depths of space, we are reminded of the importance of cherishing our unique world and nurturing it for future generations. Public interest in space exploration significantly influences educational initiatives across the globe. When people express excitement about the cosmos, teachers and educational institutions recognize an opportunity to inspire the next generation of scientists, engineers, and informed citizens. Space exploration ignites curiosity and wonder, encouraging schools to incorporate space-related topics into their curriculums, from elementary science classes to more advanced high school courses. One noteworthy effect of this interest is the increase in programs that focus on STEM education. Science, technology, engineering, and mathematics have become crucial areas of study because they are directly linked to our understanding of space. Many educational organizations actively collaborate with space agencies, such as NASA, to develop effective teaching materials and initiatives that align with ongoing space missions and discoveries. By using real-world examples from space exploration, educators can help students relate what they learn in the classroom to the larger universe. Moreover, public events, such as rocket launches or planetary exploration announcements, often culminate in heightened enthusiasm about space. This wave of excitement can lead to community initiatives, such as public lectures, workshops, and even hands-on activities like building model rockets or coding simulations. When communities engage in space-related projects, they foster a culture that values exploration and scientific inquiry, ultimately influencing the types of educational programs that emerge. Additionally, the rise of online platforms and social media has created unprecedented ways to share information about space with a broader audience. This accessibility allows schools to tap into trending topics and integrate them into lessons quickly. As educational institutions adapt to public interest and trends in space exploration, they not only promote knowledge but also a passion for the sciences, encouraging students to dream big, think critically, and envision contributing to humanity's quest to explore the universe. Preserving celestial heritage is a vital aspect of universal exploration that can significantly affect how we understand our past, shape our future, and define our identity as a species. The study of celestial bodies, such as planets, moons, and asteroids, allows us to gather critical information about the formation and evolution of our solar system. By protecting these sites, we acknowledge their scientific and cultural significance, ensuring that future generations have the opportunity to study them and glean insights into humanity's place in the cosmos. The significance of celestial heritage also extends to the legacy of human exploration itself. Many of the locations we have mapped and studied bear the marks of our curiosity and ambition, from the footprints left on the moon to the technology that enables us to send robotic probes to the farthest reaches of space. These sites become historical milestones in both human achievement and scientific inquiry, providing a tangible connection to the brave explorers who dared to venture into the unknown. Preserving such sites is akin to protecting our collective memory, emphasizing the value of exploration and the quest for knowledge. Additionally, as we venture deeper into space with plans for permanent human habitation on celestial bodies, the question of stewardship becomes pressing. With commercialization and potential colonization of other worlds on the horizon, it is essential to approach celestial environments with respect. This requires fostering an ethic of preservation that prioritizes scientific exploration while minimizing disruption to these environments. By safeguarding celestial heritage, we ensure that we do not repeat historical mistakes made on Earth, where exploitation has often led to environmental degradation. The implications of these efforts are profound. They intertwine our scientific pursuits with ethical considerations, prompting us to reflect on how we interact with the cosmos. As we continue to explore beyond our planet, recognizing and preserving celestial heritage enriches our narrative, reminding us that we share the universe with a myriad of wonders waiting to be understood and appreciated. This endeavor serves both as a tribute to our achievements and a guide for the approach we must take as humanity reaches for the stars. Advancements in technology have the power to fundamentally reshape our relationship with the universe in remarkable ways. As we develop ever more sophisticated tools, our ability to explore the cosmos expands exponentially, bringing knowledge that was once the realm of science fiction into the realm of reality. For instance, telescopes equipped with powerful imaging and data collection capabilities allow us to peer deeper into space than ever before, revealing distant galaxies, exoplanets, and the remnants of cosmic events that shaped our universe billions of years ago. Moreover, the rising field of astrobiology is becoming an essential part of our exploration efforts. With technological enhancements, we are probing Mars for signs of past life and studying the moons of Jupiter and Saturn to find possible habitats for microbial life. As we gather data from these celestial bodies, we confront the profound question of whether we are alone in the universe. The very act of searching for life beyond Earth alters our perception of our place in the cosmos, reminding humanity of our shared origins. Artificial intelligence plays a vital role, processing vast amounts of astronomical data, helping to predict celestial events, and even identifying new celestial phenomena which humans have yet to comprehend. This symbiotic relationship between technology and scientific inquiry opens doors to novel ideas and an entirely new understanding of how the universe operates. As these technologies continue to develop, the line between observer and participant blurs, allowing us to engage with cosmic phenomena in unprecedented ways. As our technological prowess grows, so do the ethical implications of our explorations. The question of how we treat other worlds and the potential life within them underscores a need for reflection about our responsibilities as explorers. Our advancements are not just about gathering knowledge, but understanding our roles as stewards of the universe, prompting us to consider what it means to be part of something so vast and interconnected. Exploratory missions have always pushed the boundaries of our understanding of the universe, revealing not only the wonders of distant worlds, but also critical insights about our strategies for exploration. One major lesson learned is the importance of collaboration. Throughout history, missions such as the Mars rovers and the Hubble Space Telescope have involved teamwork across nations, showcasing how diverse expertise can lead to groundbreaking discoveries. This collaboration fosters innovation and shared knowledge, ensuring that future missions will benefit from a rich tapestry of insight from scientists worldwide. Another key lesson is the necessity of adaptability. Missions, such as those to the Moon and the outer planets, have encountered unexpected challenges, whether it is technical malfunctions or environmental conditions. These experiences have highlighted the importance of building flexible systems that can adjust to unforeseen circumstances. Future exploration endeavors will likely focus on developing adaptable technologies that not only withstand harsh conditions, but can also make on-the-fly decisions to optimize performance. Risk management has also emerged as a vital lesson. Past missions have faced failures, and each setback has provided valuable data on what can go wrong. This knowledge helps scientists create more robust protocols for ensuring the safety of both spacecraft and crew in future endeavors. By analyzing past failures, we can anticipate potential issues and mitigate risks more effectively, paving the way for more ambitious missions, including human travel to Mars. Finally, understanding the importance of sustainability in space exploration has become increasingly apparent. As we look to explore beyond Earth, we recognize the necessity of protecting extraterrestrial environments, emphasizing responsible exploration. This growing awareness will not just shape our approach to celestial bodies, it will also influence how we manage resources in space, paving the way for sustainable practices that can sustain long-term exploration missions. These insights collectively ensure that each subsequent mission is built upon the foundation of years of experience and learning, allowing humanity to venture further into the cosmos with confidence. The universe is filled with mysteries that challenge our understanding, and among these are several unexplored anomalies that continue to perplex scientists. One of the most intriguing is dark matter. Despite making up approximately 26% of the universe, this elusive substance has not yet been directly observed. It interacts with ordinary matter only through gravity, which complicates its detection. Theoretical models suggest dark matter could consist of particles that have yet to be discovered, leading scientists to conduct experiments deep underground or in space to uncover its nature. Another fascinating anomaly lies in the phenomenon known as fast radio bursts. These brief but intense bursts of radio waves were first discovered in 2007 and remain largely unexplained. They emanate from distant galaxies and occur in a matter of milliseconds, emitting energy equivalent to that of the Sun over a time span of several days. Though various theories speculate on their origins, including pulsars and even extraterrestrial civilizations, no conclusive explanation has emerged, leaving the scientific community eager for insights. The Great Void, also known as the KBC Void, adds to our list of cosmic enigmas. This immense region of space contains far fewer galaxies than expected and spans approximately 200 million light-years. Its existence raises questions about cosmic structure formation and the distribution of matter in the universe. Researchers are investigating how such vast, empty spaces can exist without contradicting the principles of cosmology that predict a more uniform distribution of matter on large scales. Another elusive concept is the nature of gravitational waves originating from events such as colliding black holes or neutron stars. While we have confirmed their existence, the potentials and implications of these waves open up new avenues for understanding the fabric of space-time. Scientists are refining their instruments and experiments to explore these ripples in more detail, hoping they might unveil secrets about the early universe or the fundamental workings of gravity itself. The pursuit of these anomalies represents a thrilling frontier in astrophysics, promising to reshape our understanding of the universe. The investigation into cosmic voids, those vast expanses of space where very few galaxies exist, utilizes a combination of observational astronomy and advanced computational simulations. Scientists have employed powerful telescopes, both on the ground and in space, to map the distribution of galaxies throughout the universe. This mapping allows researchers to identify regions that are unusually empty, revealing the presence of cosmic voids. By examining these areas, cosmologists gather data on how the universe's structure influences the formation of galaxies and large-scale cosmic phenomena. Furthermore, exploring cosmic voids has significant implications for our understanding of dark energy and the overall evolution of the universe. Dark energy is a mysterious force believed to drive the accelerated expansion of the cosmos. Observing voids can provide insights into how dark energy behaves, particularly in regions of low mass density. Through these observations, scientists can refine models that describe the universe's expansion, leading to a better comprehension of its ultimate fate. The study of voids also intersects with investigations into the cosmic microwave background radiation. This slight afterglow from the Big Bang furnishes a detailed snapshot of the universe when it was just a few 100,000 years old. Understanding how voids formed and evolved over billions of years sheds light on how matter and energy interact at the grandest scales, connecting the early universe to the present day. By combining observational data with simulations, researchers further test their hypotheses about void formation and behavior. These models help predict how voids will continue to evolve, and what impact they will have on galaxy formation in the future. Thus, exploring cosmic voids not only expands our knowledge of the universe's architecture, but also enhances our understanding of fundamental cosmological principles. Cosmic background radiation is a remnant from the early universe, a faint glow that fills the cosmos, echoing the Big Bang. It provides an invaluable snapshot of the universe when it was just about 380,000 years old, allowing scientists to explore the conditions that existed long ago. This radiation is remarkably uniform, but scattered across it are anomalies, small fluctuations that reveal much about the structure and evolution of the universe. These anomalies point to regions of differing densities in the early universe, which ultimately contributed to the formation of galaxies and clusters of galaxies. By studying these variations, researchers can glean insights into the composition of the universe, measuring how much of it is made up of ordinary matter, and dark energy. Such investigations offer clues about the forces that have shaped cosmic evolution and help refine our models of how the universe developed. Interestingly, some anomalies have sparked discussions about the fundamental nature of our cosmos. For instance, certain features appear to contradict the expectations set by the standard model of cosmology. These discrepancies create exciting debates in the scientific community about the possibility of new physics beyond our current understanding. The fluctuations are not merely statistical noise, they challenge scientists to rethink the conditions that led to the intricate structure we see today. Continued exploration of cosmic background radiation reveals not just the history of the universe, but also the mysteries that linger within it. As technology advances, our ability to detect and analyze these anomalies improves, promising even deeper understanding of celestial phenomena. Each anomaly serves as a puzzle piece in the grand picture of cosmic history, inviting a closer look at the universe's origins and destiny. The quest to uncover the mysteries of dark energy is one of the most profound challenges facing modern science. This elusive force, thought to constitute approximately 70% of the universe, drives its accelerated expansion. To understand dark energy, scientists employ a range of methods, blending observational astronomy with theoretical physics. By studying distant supernovae, for instance, researchers have gathered evidence suggesting that the expansion of the universe is not only continuing but speeding up. These bright stellar explosions serve as cosmic yardsticks, shedding light on the properties of dark energy through their brightness and distance. Another powerful tool in this investigation comes from the cosmic microwave background radiation. This faint afterglow of the Big Bang offers valuable information about the universe's early conditions and its subsequent evolution. By analyzing tiny fluctuations in this radiation, scientists can infer the density of dark energy and how it influences the cosmos's expansion over time. A staggering amount of data from satellite missions, such as the Planck spacecraft, has been instrumental in refining our understanding of the universe's composition, providing vital clues about dark energy's role. Gravitational lensing also plays a crucial part in this intricate puzzle. Light from distant galaxies can be bent by the gravitational pull of massive objects, revealing information about the distribution of both dark and visible matter. By mapping these distortions across the sky, researchers can assess how dark energy affects the growth of large-scale structures in the universe. This method allows scientists to create a clearer picture of how dark energy impacts the cosmos on grand scales, further illuminating its mysterious nature. As technology advances, we are poised to uncover even more insights into dark energy. Future telescopes and observatories are set to improve our capacity to measure the properties of the universe and enhance our understanding of this enigmatic force. The interplay of new data and evolving theories could one day unravel the intricate web of dark energy, helping to answer fundamental questions about our universe's fate and the principles governing its behavior. As researchers delve deeper into the mysteries of the universe, they may soon uncover discoveries that fundamentally alter our understanding of reality. One promising avenue lies in the field of quantum mechanics, where phenomena such as entanglement and superposition challenge traditional notions of space and time. For instance, experiments consistently reveal that particles can be linked in ways that seem to defy the classical laws of physics, suggesting that our perception of separation and individuality might be an illusion when we zoom in at the quantum level. Additionally, advancements in cosmology could further reshape our reality through the study of dark matter and dark energy. Together, these enigmatic components are believed to compose about 95% of the universe's total energy density, yet their nature remains elusive. Discovering the fundamental properties of dark matter could lead to a deeper understanding of the structure and evolution of the cosmos, influencing everything from galaxy formation to the very fate of the universe itself. The realm of neuroscience also holds potential for transformative findings. As scientists explore the brain's intricate workings, they may uncover the mechanisms underlying consciousness and perception. This could redefine how we interpret our experiences of reality, suggesting that our consciousness may not just be a byproduct of neural activity, but instead be a fundamental aspect of existence, linking subjective experiences to the fabric of the universe. Finally, if future breakthroughs in artificial intelligence or technological convergence enable us to merge human cognition with machine intelligence, we may find ourselves grappling with a new dimension of reality, where our definitions of intelligence, existence, and even life itself are challenged. Each of these avenues not only promises intriguing discoveries, but also invites us to rethink the very nature of reality in ways that we are only beginning to explore.